Another day, another grind. Alright, let's lock in. What's up, Jason? How you doing, man? Yo, this problem is so many lines of code. Can you show your profile once? Sure, I guess. It's not that impressive, to be honest. It's not that impressive, if I'm being honest. rank 500,000. Trash, garbage. All right, let's get to the next problem. Just did. Get back to this list. Wait. Is my stream still on or no? I don't know, whatever. I feel like I should have a new session today. How am I going to remember all this? This is rough. There's too many problems. Okay. We did do range sum of BST. I skipped this one somehow, but I did it during work today. This problem was not that difficult, I feel like, but a little bit tricky, I guess. To be like super optimal. Top product, then range sum. What's after range sum? Should be after this. Yo.
Nice.
Thank you, Evasaurus. Thank you for the tier 1. Appreciate you. Alright, next question. Apparently it's easy. Given a stream of integers and a window size, calculate the moving average of all integers in the sliding window. Implement the moving average class. Moving average initializes the object with the size of the window size. Double next returns the moving average of the last size values of the stream. Okay, what's an example? Moving average 3. Next 1. Next 10. Next 3. Next 5. I feel like the way I think about this, I would probably go with having some sort of a size variable and also like a current average variable, or just average. And this way we can literally just not have to, like, I was thinking initially like we're gonna append to an array and stuff like that, but we'd have to traverse through the array O of n times. That's pretty inefficient. The next should return the moving average, and this is done in O of 1 time because we're not storing or traversing through anything. We're only storing the variables that we need to calculate this thing. So my first thought is, what does this 3 mean though? Initialize with the size. Oh, I see. Yeah, we do have a size. Okay, so the size is that. Oh, wait a minute. I guess we can initialize the array to be that size then. Then in that case, that's not true. That's not true. We just need to, well, No, I think we could still do this pretty efficiently, actually. If we have a deck, double end a queue. Like, let's say we start with the size of 3, right? So we add 1, then 10, then 3, right? We can also still keep track of an average variable, which will subtract. So like if a new one comes in, right? So like let's say a 5 comes in, all we have to do is just subtract 1 from the average, which we can easily just pop left, right? I guess getting the length of the queue is always O of n time. Can we really do better than that though? I don't know. I'm not sure about that. I feel like no. Double next returns the moving average of the last size values. I'm just overthinking it. Maybe like the naive solution surely is not good enough. I mean, that's the thing. We only need to keep track of this deck. I think this deck works completely fine. So self.q will be this, and actually no, it'll be initialized as a deck. Self.size is equal to the size. I don't know how I just removed everything. And we'll have the self.average is equal to 0. Which is going to be calculated as we increase things in the deck, right? So, the thing that I'm like a little confused about is that if I do this, I won't have a size for the first 2 cases. I'd have to look through the length of the array, which is, I guess, like non-negligible, but it will still be O of n time if, let's say, n is really big. In this case, we're going to somehow need to figure out you can just have a cur size, right? This is like this. Oh my god, I accidentally submitted by accident. Rolling. You can just have cur size, which can initialize to 0, and that's fine. Which I don't know if there's a cleaner way to do this. But we do definitely need a max size, and cur size allows us to not have to depend on the length function for the array, which could be expensive. I am being consistent on Leetcode since 3 days. That's good stuff. Good stuff. Just keep it up. If you keep it up, you'll get better and better every day. That's for sure. Alright, so what I'm thinking is that we can, anytime we call the next, we'll have cur size plus equals to 1. And then our self.cur size is equal to 1. And self.q.append cur size, or sorry, val. So we add it to the val, and now we check, right? If, let's keep it simple for now. We'll just check it on the calculations. Self.average is equal to I also need a current sum, I feel like. I don't see anything bad with having a current sum, if I'm being honest. Because this self.cur sum will allow us to val, right? So now cur sum is set to 1. And all we got to do is just simply divide, right? So self.average is technically just equal to the self.cur sum divided by the self.curse size. We could just always do it like that, I guess, which means we don't even need this average variable. We can just always return whatever we calculate from all this. So we can return self-curse sum and curse size. Now the thing that we have to consider, right? Anytime we add something to the array, like for example, in this case, let's say the window size is 2 or 1 even, right? If we had a 1 and then a 10, we add the 10 first, but then we check here if self.curse size is greater than self.size, which is technically, I should have named it max size. And then what we actually have to do is update self.curse size minus equal to 1 and self.curse sum minus equal to q.pop left, which will give us the value of the leftmost element. So we're going to notice subtract 1. So if we add this 10, the curse sum should have been 11. And then by this point, we subtract the 1. So now the curse sum is back to 10. And then we can just simply return. And I think this solution should work. Oh, sorry. I'm going to refer to the self.q. It's too easy. It's too easy. This question is easy though. So let me ask ChatGPT if I can optimize this somehow. Welcome back, Jason. Is there anything wrong with this? There's a minor redundancy. Hold on though. Isn't using a self.curse size more efficient than using the length? Because length is O of an operation, no? And curse size would be constant. It's an O of 1? Oh, because it already accounts for that. Oh my god. You know what? My bad, Python. My bad, Python, for doubting your... Oh my god. Okay, my bad. We don't need any of this then. So then this is... All this needs to be is if self.q.length, or sorry, length of self.q is greater than, then this should be the same. Not curse size, then actually the length of self.q. Same thing. Same thing. It's actually more efficient too, I think. But I mean, maybe it's around the same. But DeepSeek better than ChatGPT. I actually should try the other ones out too. I don't know why. I don't know. I guess I'm just familiar with ChatGPT and I paid for it, so I guess I'm a little more biased perhaps, but I should consider other options too though. I don't know about now though. I don't know about right now. Maybe I should. I don't know. When AI? Not sure though. I mean, yeah, I think some, even like Claude is good, or even Copilot I think is good too. I haven't tried them all, so I don't know. I don't know. Okay, so let me restart this problem and not care about the length case, because in the length, I actually didn't know that, but apparently length of a deck is constant time because it already has an internal counter. So I'll keep that in mind for the future. So if I were to just approach this problem again, we can create a queue, a deck. Once we have the deck, add until size. So self.queue is equal to the deck of this. Self.size is equal to size. What else do we need? Self.curSum is equal to 0. I think that's it for now. And so if we add one, do a self.curSum plus equal to val. And then we'll also self.queue.append val. And if at any point length of the self.queue is greater than the self.size, then we need to self.curSum minus equals the self.queue.pop left. And that'll bring our sum back and also keep our length of our queue sane. And then by this point, we can just simply return self.curSum divided by the length of self.queue. Easy ass problem, bro. Deck. Paying for GPT-4? I do. I don't know if I'm getting scammed, but I do it. Next permutation. Oh my god, this problem I think I've done before, but I'm not gonna cheat. A permutation of an array of integers is an arrangement of its members. Oh my god, I think I remember this problem. No, this problem is cancer. Fudge. Oh, I remember this problem. No, the algorithm for this, no one will ever figure this out on their own. I remember watching this. It's some random ass algorithm and I don't even know why it works. I just need to memorize why or what the algorithm is. I remember this one.
Hello, and welcome back to the Cracking Fang YouTube Pivot.
I took control, went solo, and built my own online night empire.
Hello, and welcome back to the Cracking Fang YouTube channel. Today we're going to be solving Leetcode problem 31, next permutation. Before we get into the solution for this, I just want to say I hate this problem.
I hate this problem. Imagine hearing that from somebody that's already in meta.
Hate, hate, hate. This is my least favorite problem, and I just want to say I know how to solve it. I know the solution, and I think I can explain it pretty well, but if you...
Dude, if somebody asked this in an interview, I swear I think you're just doing it to fail people. Like, it's been asked 33 times apparently by Meta in the past 3 months. Like, they do not want you to succeed, I feel like, if they ask this question. Genuinely.
If you want want a deep understanding of the intuition behind it, sorry, I have no idea.
I have no idea, he says.
This is just one where I understand it enough to get through, but if you want a proof of why it works, this isn't the video for you. I can't do it. I hate this problem. So, that being said, let's read the question prompt. It's quite a mouthful. A permutation of an array of integers is an arrangement of its members into array of permutation. Next permutation of array 2, 3, be 2, 3, and after this. Simple. We need text here. Okay, we read the question prompt and we looked at a very simple example, but unfortunately, it's not really going to be that straightforward because the numbers are usually going to be a little bit trickier, and it's hard to actually derive what happens when you look at the basic example of 1, 2, 3. It doesn't really tell us how to do it. So let's think about the two cases that can happen in this problem, which the problem description tells us. The first is that there actually is no next permutation, and this is the case where we have something like 3, 2, 1. Because this is already the largest number we can get by rearranging these three numbers, the next permutation is just going to be the wraparound. So basically, it becomes the smallest number we can get. So if basically our input is sorted in descending order from left to right, then we just return the reverse of our input, and that's our answer. So that's the first case that you need to take care of. The other case is when you actually in if process. The first is that there actually is no next permutation, and this is the case where we have something like 3, 2, 1. Because this is already the largest number we can get by rearranging these three numbers, the next permutation is just going to be the wraparound. So basically it becomes the smallest number we can get. So if basically our input is sorted in descending order from left to right, then we just return the reverse of our input, and that's our answer. So that's the first case that you need to take care of. The other case is when you actually need to find the permutation. So let's look at 1, 4, 5, 8, 7, right? This is our number. What is our next permutation here? Well,
1, 4, 5, 8, 7. Then I think it would be 1, 5, 4, 7, 8.
Well, we can see that if we swap the 7 and the 5, we'll get...
Oh, that's right. You can make 1, 4, 7. But then it should be 5, 8.
The next one, because right, we want to swap, and then we also need to swap the 5 and the 8 after we do the swap. So it would be 1, 4, 7, 8, 5, 8 is the next larger number, right? So how did we actually do this? What we want to do here for this problem, and again, I'm sorry, I don't know why this works.
What's up, people? How you doing?
I can't give you the proof for this, but I can just tell you how to solve.
Where's our radiant Leetcoder friend? I don't know. Listen, I don't think he pops up anytime I stream, but I'm sure he'll pop his head out whenever he feels like it.
Solve this problem. What we want to do is we want to find the point in our array where it stops being increasing, starting from the left, right? So we can see that 1, 4, 5. We basically want to find the point where the array stops being sorted. If it is even sorted at all. It could just be that it's not sorted, in which case that's fine. I guess the first number would just be sorted. And we'll call the number where the index where the array stops being sorted as our pivot. So in this case, 8 is our pivot here. 5 is the pivot, apologies. Because at this number, this is the final value that is in sorted order, right? 7 and 8 are not in sorted order. So we need to make some swap with 5, with one of these numbers here that's not in sorted order. And what we want to do, and the way we're going to do this, is we're going to start from the right, and we're going to go left. And basically, we're looking for the point where nums of I is actually greater than nums of I minus 1, right? So this would be this 8, right? Because that would imply this is when the first point where the array stops being increasing, starting from the left. Sorry, so going from the right, apologies. So we will identify our pivot as this 8. So basically, this is the number where it stops, I guess, increasing as we're going to the left. And our pivot is actually the index before it. So it's going to be this one. So the point where nums of I is actually greater than nums of I minus 1. So this becomes our pivot. And then what we want to do is we're going to start from the right again. And what we want to do is we want to take the first number that is greater than our pivot. And the reason we want the first number that's greater than is because that will be the smallest possible number that we can swap with. And the reason that this works is, remember, we're going from left to, sorry, fuck, I keep saying the wrong way. We're going from right to left, and we're finding the first point where the array going from right to left is not sorted. So because this portion is sorted in, I guess, increasing order, right? It's going up as we go to the left.
What is it about Chamberlain University that makes our nursing students so successful? The opportunity to learn from anywhere.
When we swap this, this will be, whatever that first number is going to be the smallest possible one that satisfies, our next permutation condition here. So what we do is we swap it with the first number starting from the right that is bigger than the pivot number that we've identified earlier. So let's do that swap. So we'll say 1, 4, 7, 8, 5. now, unfortunately, this isn't our answer, right? We need to swap the 5 and the 8. And remember that this part of the array after the pivot was sorted before in increasing order like we saw. So that means that if we actually reverse this array, right, we'll actually get this part as the next smallest one, right? Because if this is sorted in increasing order, if we then reverse it, then it's going to be sorted in decreasing order, which is the next smallest arrangement of these numbers. And if this doesn't make sense, I invite you to play around with this. Remember, the first thing that we're going to do is we're going to find the pivot. And again, these diagrams suck, and I think it's much easier to look at this in code and kind of get what we need to do. But essentially, we want to find the pivot index, and then what we want to do is we want to swap with, I guess, first num to the right of pivot, such that, let's see, the num is greater than, yeah, it's just greater than the pivot, right? And that's going to be our swap. And then we just need to reverse, so reverse to the right of the pivot, and that will get the right side of the array after the pivot in the right order. And remember, the reason that we do that is because we are going from right to left, looking for the point where this array stops increasing, right? So we go from 7 to 8 because that's increasing, but then when we hit the 5, it stops increasing, so this is our pivot point, and we swap it with the first largest number greater than 5 to the right of the pivot point. So the first largest number to the right of 5 is going to be the 7. Then we need to just reverse this because remember this part was sorted. That was kind of our original search condition here. And then once we reverse this, we'll have it in the right order because now it'll be in that sorted order, and now we'll have our next permutation, which is our answer. Again, I don't know how to prove that this works. I just know that this is the solution and this is the most optimal way to do it. This is the best I can do, I'm sorry. So let's actually go write the code. Hopefully that will make things clearer. And if it doesn't, I don't know, maybe go play around with the diagrams. If you have Leetcode Premium, go look at the solution. Maybe you can read it and understand. This is just one of those questions. Like I said, I absolutely hate this problem. It's terrible. How you're supposed to figure this out on an interview, I have no idea. You're probably going to fail if you get this and you haven't memorized it. So yeah, I have no idea. I hate this problem. So let's actually go to the editor and write this out and be done with this abomination of a problem. Okay, we're back in the editor. Let's write the code for this so we can be done with this abomination of a problem and we never have to see it again. So remember that we need to look for the pivot point if it exists. Remember, it can possibly not exist in the case that we have something like 3, 2, 1, where there is no pivot, and all we need to do is simply reverse the array. So let's say our pivot is going to be equal to none, because in the beginning we don't have one. And remember, we're going from right to left, looking for the point where the array going from right to left stops increasing.
Yeah, you're probably gonna fail if you've never seen this problem before. I feel bad for the people that get this question and have never seen it before.
Fuck, I keep saying the wrong way. Works is, remember, we're going from left to, fuck, I keep saying the wrong way. We're going
That is funny.
from right code, I think it will never have to see it again. So remember that we need to look for the pivot point if it exists. Remember, it can possibly not exist in the case that we have something like 3, 2, 1, where there is no pivot, and all we need to do is simply reverse the array. So let's say our pivot is going to be equal to none, because in the beginning we don't have one. And remember, we're going to be going from right to left, looking for the point where the array going from right to left stops increasing when it's going right to left. So we're going to say for I in range, len nums -1, and remember we're going to the left, we're going to the 0th index this time instead of -1, because remember we're comparing with the, or comparing index I with index I minus 1, so
That's
we
right.
can't actually go to that final index because we'll have an out of bounds error. So we're going to say if nums of I is actually greater than nums of I minus 1, then what we want to do is that is our pivot point. And remember that it's the index -1, the pivot is the actual number that is the smaller one. So for example, like in our code, I think it was, what did we use? So we used 1, 4, 5, 8, 7. So we go from the right. Okay, is nums of I, so is 7 greater than 8? No, it's not, so we keep going. Is 8 greater than 5? Yes, so that means that our pivot is actually going to be this 5. So we want to say that our pivot equals to the I minus 1. And at this point, we found the pivot, and we can actually break out of this loop. Now what we want to do is we want to add an else statement to our for loop. And if you don't know how else statements work with for loops, essentially, if the for loop completes, if it goes through the entire iteration here and doesn't return or break or some sort of, exit out of the loop early, then this else condition gets run. So in this case, if we go through the entire array and we don't find a pivot, that means that the array from right to left is actually increasing the entire time. So this is in the case we have 1, 2, 3.
That's crazy. I've never seen a for loop like that.
Right?
That's wild. I don't think I'd ever write it like that, but... Find the first decreasing element, then find the first value greater than the first element. Swap. Reverse the sublist. How the hell are you supposed to know that?
that means that it's sorted in increasing order from right to left, which is that case where we actually don't have a pivot. So in this case, all we need to do is actually just nums.reverse and then return. And it actually tells us not to return anything, we just modify nums in place. So sorry, just modify it and then we just return. Now what we want to do is we found our pivot. Now we need to find that first point that's actually the first number to the right of our pivot. It's greater than pivot, and we can make the swap. So in this case, it's a 7. So what we're going to say is we're going to say swap, and this is going to be the index of the swap. We're going to say length of nums minus 1, and we're going to say while nums of swap is actually less than or equal to nums of pivot. Remember, we're looking for the first number from right to left that is greater than the pivot, because this is the next biggest number that we want to swap with to get the smallest number when we actually, return our permutation here. So while, we have numbers that are, less than our pivot, obviously it doesn't work that way. So if we swapped it, we'd get a smaller number, and we can't have that. We need the next bigger number. So we need to find the smallest possible next number we can. And because the array is sorted from right to left, as we kind of established in this part, the first number that we find from right to left that satisfies our condition will be the one that we want to swap with. So we want to basically, until we find that point where this is no longer true, we just want to decrement swap. And we're guaranteed to find it in this part of the array. So now what we need to do is actually swap the numbers. So we're going to say nums of pivot. Remember, pivot is our actual index, not the number, and then swap is also the index. So we need to swap these. So we're going to say, nums of swap equals to nums of swap, and then nums of pivot. So we're going to swap these two. And then what we want to do, we want to say nums. Remember that after we make the swap, so 7 gets swapped with 5, we need to swap this part of the array. Oh, sorry, not swap. We need to reverse it, so that way we can get the order. Because remember, this part is sorted in, increasing order as we're going from right to left. So to get it in the smallest possible representation of these numbers, we just need to reverse it, and that will have it in the opposite order.
Thank you.
And then we're basically done. So we want to reverse everything from the left of our pivot index. So we want to say nums of pivot plus 1. Everything to the right of that, we want to say revert is going to be equal to reversed nums of pivot plus 1. Basically, we just want to reverse everything to the left of the pivot. And that's all you need to do. We just return here. Let's actually make sure we didn't make any bugs anywhere and submit this. And cool, we see that it runs. So, what is the time complexity for this algorithm? Well, in the worst case, we're going to make one entire pass through our array. And this is going to be the case where essentially we need to, break out of this loop to the left, which is that case where we actually don't have a pivot. So in this case, all we need to do is actually just nums.reverse and then return. And it actually tells us not to return anything, just modify nums in place. So we modify and then just return. Now what we want to do is we found our pivot. Now we need to find that first point that's actually the first number to the right of our pivot that's greater than pivot, and we can make the swap. So in this case, it's the 7. So what we're going to say is we're going to say swap, and this is going to be the index of the swap. We're going to say length of nums minus 1, and we're going to say while nums of swap is actually less than or equal to nums of pivot. Remember, we're looking for the first number from right to left that is greater than the pivot, because this is the next biggest number that we want to swap with to get the smallest number when we actually return our permutation here. So to get this greater than the first n, or while nums of swap is actually less than or equal to nums of pivot. Remember, we're looking for the first number from right to left that is greater than the pivot, because this is the next biggest number that we want to swap with to get the smallest number when we actually return our permutation here. So while we have numbers that are less than our pivot, obviously it doesn't work that way, because if we swapped it, we'd get a smaller number, and we can't have that. We need the next bigger number. So we need to find the smallest possible next number we can. And because the array is sorted from right to left, as we kind of established in this part, the first number that we find from right to left that satisfies our condition will be the one that we want to swap with.
The 5.
So we want to basically, until we find that point where this is no longer true, we just want to decrement swap, and we're guaranteed to find it in this part of the array. So now what we need to do is actually swap the numbers. So we're going to say nums of pivot. Remember, pivot is our actual index, not the number, and then swap is also the index. So we need to swap these. So we're going to say nums of swap equals to nums of swap, and then nums of pivot. So we're going to swap these two. And then what we want to do, we want to say nums. Remember that after we make the swap, so 7 gets swapped with 5, we need to swap this part of the array. Sorry, not swap. We need to reverse it so that way we can get the order. Because remember, this part is sorted in, increasing order as we're going from right to left. So to get it in the smallest possible representation of these numbers, we just need to reverse it, and now we'll have it in the opposite order.
Old Spice. Smells super 24/7. No, it's not the deli. It's Oscar Mayer Deli Fresh.
And then we're basically done. So we want to reverse everything from the left of our pivot index. So we want to say nums of pivot plus 1. Everything to the right of that, we want to say revert is going to be equal to reverse nums of pivot plus 1. Basically, we just want to reverse everything to the left of the pivot. And that's all you need to do. We just return here. Let's actually make sure we didn't make any bugs anywhere.
Okay, the solution I have here is pretty nice. So basically, you create a pointer on the right side. So let's run through an example. Let's go through an example here, right? Simple 1, 2, 3. Or let's actually go through his example, which was 14587. 4587. So logically speaking, the next biggest number, if I were to just look at these numbers, is 758, no? 758. So I guess like the thing you notice is like how are you supposed to know that this pointer should swap with this pointer? That's like the thing you're supposed to figure out. And then once you do that, how do you know? Because like once you swap these, technically what ends up happening is the result is 4875, which still technically doesn't match this final result. And then I guess you're supposed to know to reverse everything after the pivot. I guess you're supposed to just know that. So I guess let's try to code this from scratch. Okay. So the first thing that I would think of doing is it seems like we need to find the first value that is less than the last value. So in this case, I'll just have an I pointer that starts with the length of nums minus 1. And then while I is greater than or equal to 0, we'll decrement if we don't find it. And we'll simply look for whether or not actually I has to be greater than 0, because if it's actually 0, we can't check an index of a -1. So it has to be greater than 0. Otherwise, we have not found it. So we check if nums of I is you gotta find the first decreasing element. That is like not that intuitive, but so if nums of I minus 1 is less than nums of I, then that means this is a decreasing element, right? So then we have found our I. We can break here. The thing is, if we break here, that means that we found. So like, let's say we're going through this 7. This is I, right? So is 8 less than 7? It's not. So we move I left. So then is 5 less than 8? It is. So we're gonna break. So technically, our I minus 1, I guess we could just decrement it again, just for the sake of making sure that we're actually on the pivot. So I is the position we are supposed to, is supposed to be the swap, and then we find the first value. I mean, also the edge case is that if I is equal to return reversed nums. That's the edge case. If not, then we're valid here so far. Everything can go as we kind of set up. But this second step, find the first value greater than the first element. I don't know what this means. Decreasing element found. Someone says a moment of silence for the poor soul that gets this interview question without having seen it before. That is crazy. I get finding the first decreasing element, I guess. But then once we do that, finding number just larger than 4 makes no sense. How are you supposed to know to pick 4? That's the thing I don't understand. I don't get the second part.
The index of the swap. We're going to say length of nums minus 1. Then we're going to say while nums of swap is actually less than or equal to nums of pivot. Remember, we're looking for the first number from right to left that is greater than the pivot.
The first number from right to left that's greater than the pivot. I see. Go from right to left again and find the first value that's greater than the pivot. So if that's the case, then what we want to do is, again, we have a second pointer which starts at the end. So while j is greater than 0, or I guess in this case, while j is greater than I, because it shouldn't ever go past I, j minus equals 1 if we don't find it. If nums of j is greater than or equal to, or just greater than, seems like greater than or equal to nums of I, then it counts as a swap. Do we swap within this if case?
Because it's the next biggest number that we kind of... After we make the swap...
I see, I guess he just does it after. Actually, yeah, I could just do it like this. While that's better, it's cleaner to write it that way. While nums of j is less than, how did you write it? And then at this point we found it. So if we found it, then all nums of j is less than or equal to. So we found it. We are going to swap now, right? So nums of I, nums of j is equal to nums of j, nums of I. So we just performed the swap here, right? And if we just perform the swap, then at this point, we need to reverse the rest of the array. So from nums of I to the end is equal to nums reversed of nums of I to the end. Frick. I must have said it wrong.
So basically, we just want to reverse everything to the left of the pivot.
The left of the pivot.
And that's all you need to do. We just return here. Let's actually make sure we make any bugs anywhere.
Return? Do I really need to return? I don't think the return is technically necessary. What is wrong here, actually? I'm confused. I actually wonder if this is not needed. Maybe it's not? Okay, I'm trolling, I guess. How did I write this before? Oh, they reverse everything after the pivot. I see, that makes sense. Okay, I'll redo it, I guess. So technically, you start with I is equal to the length of nums minus 1. And what you want to do is while I is greater than 0 and nums of I is greater than, is it greater than or equal to? I actually don't know. If it's equal, I guess it qualifies. I don't know. This is I minus 1. And then if I is equal to 0, nums, reversed nums should pass for one case, right? Nums is equal to reverse nums. Okay, that's not how to write it, I guess. Sorry, it's nums not reverse. That's how to write it. Alright, that's still not how you write it, apparently. I don't understand how I'm so dumb. If I minus 1 is greater than or equal to okay, so it has to be, why does it have to be, because you have to find the first decreasing element, right? So if it's still not decreasing, which means what does it mean to say the first decreasing element, right? So if it's greater than 0 and nums of I is greater than nums of I minus 1, nums of I is greater than nums of I minus 1. Well, yeah, I guess that's the same thing as implying that it's not increasing, right? This is not the same thing. It's not, though. Oh, what the hell is wrong with this question? I'm so confused what the algorithm is.
So we need to find the smallest. So we use going from right to left stops increasing when it's going right to left. So we're going to say for I in range, len nums minus 1, and remember going to the left, sorry, we're going to 0 index this time instead of minus 1, because remember we're comparing index I with index I minus 1, so we can't actually go to that final index because we'll have it out of bounds there. So we're going to say if nums of I is actually greater than nums of I minus 1, then what we want to do is that is our pivot point. And remember that it's the index minus 1, the pivot is the actual number that
If nums of I is greater than the previous. Oh.
is the smaller one. So for example, like in our code, I think it was, what did we use? So we used 1, 4, 5, 8, 7. So we go from the right. Okay, is nums of I, so is 7 greater than 8? No, it's not, so we keep going. Is 8 greater than 5? Yes, so that means that our pivot is actually going to be this 5. So we're going to say
How many Leetcodes did I solve? Guess about 238. But this is over like the course of many years. I feel like I've been very on and off. Like, it's not very consistent throughout the year. Find the first decreasing element, right? So this basically just means while I is greater than or equal to 0 or greater than 0, right? And well, the thing is, once we find the first decreasing element, we can stop, right? So the thing is, anything else, right? So if it's like 8, 5, that qualifies. So if it's 8, 8 or 8, 9, that doesn't work. So that means nums of I minus 1 is greater than or equal to nums of I. And this would actually work. That's the reason why this works. And then I guess the logic behind that is once we find that, we're actually at, so how did you start or get into Leetcoding? Sorry for making dumb questions. No, it's not a dumb question. Just get started, I think, with getting comfortable with data structures. But to be honest, I think it's just good to like look at the answer key a lot of times in the beginning. Obviously start with like I think Leetcode has a probably like a really good roadmap if you want to start somewhere. I think he gives like a good progression into like how you should go about in order of complexity. Because you definitely don't want to start with like the more advanced concepts when you're starting out, because you still have to learn like the foundational data structures. So just go with the Leetcode IO roadmap. I hope you can type in Google just Leetcode roadmap. Unfortunately, I can't copy paste that easily, but you could just start with the beginning, right? And then like go through them, and if you get stuck, that's fine. I think in the beginning you should just literally look at solutions, because you don't know any patterns, so you gotta kind of build that and then like learn as you go. I'd say is probably the fastest. Otherwise you can also get into like this analysis paralysis where like you'll just study data structures forever and never leak code, and you'll never feel like you're ready. But I think it's just easiest to just get started and just start doing it, because you'll get better for sure as you do it. Hopefully that helps. Okay, so now that we have our pivot, right? So we find the first thing, in this case, is I minus 1 greater than or equal to nums. It's not. So I actually stops here. But the thing that we want to swap is actually I minus 1. So we're going to have a J pointer. And we're going to do this again. And while J is greater than or equal to I, and or maybe I should just say greater than I, and nums of J is greater than nums of I minus 1, or I guess I should say less than or equal to nums of I minus 1 and J minus equals 1. Once we found this pointer, then we can actually perform the swap here. So nums of I minus 1 and nums of J is now equal to nums of J, nums of I minus 1. And then from here on out, we can simply just reverse the sublist. So from nums of I to the end is now going to be equal to reversed nums of I to the end, and this should give us our answer. Oh, I don't know where this came from. Boom, easy. I feel like this is one of those questions I might just have to like look at right before the interview. This one's low-key a little cancer, but I mean, I'd have to talk through it, of course, which is kind of the hard part. I don't even know how it's intuitive necessarily to know that you have to reverse the end of the sublist. Oh my god. I don't think it's that intuitive, if I'm being honest, but I don't know if it's even worth it to... It's just crazy how many of these companies actually ask this question. It's just cancer. I don't know how this is actually an indicator of how smart you are. It's just literally how much you don't touch grass. Like literally. That's what they're looking for. They're looking for people that never see sunlight. This question is so dumb. Alright, so I guess let's talk through it again just to say that it makes sense. But let's go to like 1, 5. 1, 4, 5, 7, 8. Or I should say maybe 8, 7. So we should actually, first thing, so the answer for this, we should just know, is supposed to be the next biggest number, right? So which is 14758. This is our final answer for the next permutation. The thing is, like, how do you get there, right? The first thing I guess you're supposed to notice is that the 7 swap, right? And then like the question is, how do you figure out that the 7 swap? It's a little confusing, I guess, how you're supposed to know that, but I think at least you can just say that the 7 swap, right? Because in this case, we'll just say that we'll create a pointer again for the length of nums minus 1. And then while I is greater than 0, and I guess if the thing is, we need to find the first decreasing element, because the one thing I noticed is that it didn't swap with the 8, but it swapped with the 5. So if I were to just kind of figure out, you know, what is the difference between the two, I can notice that 7 is greater than 8, but it's less than 5. So I guess we can go off the intuition that we're just basing it off the first decreasing element. And if it's the first decreasing element, then we can base it off of moving our left pointer based on the fact that nums of I minus 1, if the previous is greater than or equal to nums of I, then we want to keep going, right? Because the 8 is greater than or equal to 7, so let's decrement again. And then in that case, once we hit 5, or we're at 8 and 7, or 8 and 5, sorry. So we're at 8 and 5. So 5 is actually less than 8, so we get out of here. So our I pointer is actually currently set right here, right? And then from there, there is also the edge case, right? If we actually do end up hitting, if I is equal to 0, we can simply return nums.reverse, and we'll return that as the answer, because if it's 3, 2, 1, it's just 1, 2, 3. That's one thing to know, because in this case I will go all the way to the 0th position, and then that will we can consider I guess the edge case there. But for all other cases, we're still going to need to perform that swap, which from here we'll create now a J pointer, and we're going to find the first element that's actually greater than the swap, right? So let's find the first thing that's greater than the 5. So in this case, while J is greater than I, and the condition is that nums of J has to be greater than, but if it's less than or equal to nums of I, then we gotta keep going, right? So J minus equals 1, and once we're at this point, we gotta swap the 5 and the 7. So again, we're gonna write down nums of I minus 1, because we're technically 1 after, and then nums of J, nums of I minus 1. And then at this point, we got to reverse the sublist. And then at this point, we can simply just say nums of I to the end is equal to the reversed of nums of I to the end. And that will be our solution. Boom. Wait, I got it wrong. Is it just this? The freak? Oh, it must be this. I'm supposed to compare numbers of I minus 1. I'm trolling. Yeah. Whoops. Just gotta be careful with the pointers a little bit, but this problem is cancer. Can't lie. I guess I gotta really make sure I have this algorithm down though. So the point of this algorithm, the order of which you do things, 1, go right to left, find the first decreasing neighbor. 2, handle edge case. If I is equal to 0, just reverse the list. And then swap or create second pointer and find the first element that's greater than the pivot or the swap. Swap, then reverse sublist. It's not easy. This one's not easy. All right. Okay. Custom sort string. I know, even I noticed it. Okay. Let's take a little break, I guess. Let's take a little break. How's everybody doing? Pretty good, chilling. It's good, it's good. Glad to hear that. Glad to hear that. Damn, somebody just wrote how I got a 480k Fang offer with 2 weeks of prep. Oh, wait. Oh, this guy would cheated. apparently a lot of people cheat. When was my interview again? I don't know yet. I didn't schedule it yet. Don't be a cheater. Nah, I don't think I'd cheat for this. I don't know how you would actually cheat. I mean, I'm sure I could like research, but I don't think it'll do any good. But apparently Meta is like trying to go away from Leetcode. That's what I'm hearing. And apparently they're trying to move away from Leetcode by the end of year. So I don't know if I'm gonna get screwed over. Yeah, somebody posted Meta will let some job candidates use AI in their coding interviews, which is insane. Which is low-key kind of nice, I guess, because... But I don't know if this only applies to like AI engineers, though. What is it? What am I doing? I'm studying. I'm just studying, but I'm taking a break right now. Open book test. I mean, that is kind of how it should be, though. Like, if we're being honest, it's like, it's kind of stupid to test someone's capabilities just strictly based off of like how good you are at like memorizing Leetcode patterns, you know. At the end of the day, like, it doesn't necessarily reflect how good you are as a candidate, like whether or not you can do the job well. I mean, it's just like SATs, obviously, right? Like SATs, like just having a good score doesn't mean you're necessarily smart. You could have just studied like the crap out of it. Google engineer dies after being struck by a falling tree branch. What? What the hell? What the hell? Oh my god. Meta is paying $1 billion for a single individual. Oh my god. $1 billion? Yeah, I swear, I said this to my friend today. I feel like engineers are low-key is like it's like sports, you know? People try to like poach other players, but I guess in this case other coders. It's crazy. All right, whatever. That was enough of a break. Let's get back into it. Go. All right, we're looking into custom sort string. You are given two strings, order and S. All of the characters of order are unique and sorted in some custom order previously. Permute the characters of S so they match that order, the order that order was sorted. More specifically, if a character X occurs before character Y, then X should occur before Y in the permuted string. Return any permutation of S that satisfies this property. Order CBA S ABCD, output CBAD. I see. CBAD. BCAFG. BCAFG. Okay. with this problem, I'm thinking, I feel like the naive approach would be to just, you know, go check B, right? Does B exist in the string? If it does, add it to the output, then do C, then check C. But the thing that is not good about this solution is that it is inefficient, because we'd have to do this basically O to the S time. Not very efficient. Basically an O of n squared type of solution in a way. With that being said, I think we should actually do oh wait. Okay, so I guess so they're saying that if D is not in the order, so if the letter is not in the string, it doesn't matter. As long as you preserve the order, that's all that matters, right? That's interesting. So it could have been D, B, C, A, or B, C, A, D. That's whatever, I guess. And I don't even think the order matters either for anything else after the order or before the order. So I guess the thing to note is that I was initially thinking maybe we just map. I was thinking of a hash maybe, but also maybe considering it with a queue of some sort, because like we need to figure out some sort of priority. Because the thing is, like, if we just said hash, right, like, and we just mapped based on the letters, right, C is 1, A is 1, and F is 1, and G is 1. So that's like the order, right? And then if we had A, B, C, D, we could also do the same thing, actually. And in this case, like, we could just decrement any time, right? If low-key, we could just, like, even if it was like A, B, C, C, D, I think we just literally exhaust whatever that value is. The thing that makes this problem maybe a little bit trickier is that just this alone with the hash map doesn't allow you to get the value in order of priority. And I guess the only thing I'm thinking of is that in tandem we could implement some sort of a queue or a stack. Nah, queue, right? Probably queue makes the most sense, right? Because at this point we can literally just go by order: B, C, A, F, G. Now the question becomes like, oh, it does say all the characters in order are unique, so low-key this works, because I was actually concerned about the case that maybe you could have like CC, AC or something like that, but if it's all unique, then I think in this case we can preserve the order, and I think this should work. Low-key, I think the solution is valid. And if we do this, this is an O of n time, because we'll have to loop through once through the string and order to create the dictionaries for both of them. And then I guess for the queue as well. But then at this point, we can simply have we can have a result that we keep appending to anytime we have a valid string. Hello bro, I'm new subscriber. Thank you for subscribing. How to learn Java for placements. Java, I don't know what to tell you. To be honest, I don't know what the best resources are for learning Java. I mean, I think it really doesn't matter too much where you learn it. But I guess if I were you, I would probably recommend actually Python if you are open to the idea. I feel like Python is the path of least resistance, you know? There's just so much boilerplate, I think, with other languages that Python doesn't have, which allows you to have more time to process your thoughts and write code easier in an actual interview setting. So, I mean, it's your choice at the end of the day, you know? Okay, so why don't we go with this approach, right? So we're going to create the queue like we said, and then we also said the ordered dict is going to be initialized, and low key, I think we can simply just use the counter function of order, and then we can also just do the s dict is going to be the counter of s. Can a fresher get roles based on cloud and DevOps? I don't know what you mean by fresher. Do you mean like freshman? Or like a new person fresh out of college? I mean, to be honest, I feel like I don't know what the market is like if you're a college student now, if that's what you're saying. I do hear that the market is harder for new grads. So unfortunately, I don't know if I can relate, but I will say, like, if you don't have anything like in terms of job experience, I think the least you can do is try to like create projects for yourself, and have that in your resume. I think that's good to do. You have internships. I mean, I think that's good too. Like, I would definitely put that on your resume and, you know, like try to use that experience and leverage that as, you know, indicators that, you know, you could tell your interviewer, like, you know, you gained a lot of good experience. You got to obviously sell yourself. I feel like that's a part of the process. But even if you didn't learn anything from your internships, like, I think you should try to frame it in a way that you did, you know what I mean? Because I'd say sometimes you gotta fake it till you make it, honestly, even in the beginning, because like how can you prove anything, because like you don't have any experience. But obviously I would say, like, you know, still, you know, be very well versed in your field and try to do like any projects that are relevant to your field if you can. And if you can showcase that, right, and you have a lot of confidence and knowledge in that space, I think that's, you know, good for the interviewer to see, and they'll be like, oh, even though this guy didn't work anywhere, like this guy knows what he's talking about, right? And I think those are good things to do. Hopefully that helps. But I mean, to be honest, like, it's not going to be easy. I think like anything with, you know, searching for a job is really just a numbers game. So you're just going to have to apply like crazy, I feel like, and just, you know, be okay with the rejections and keep going until you find one, because all it takes is one, right? Like, you will get one eventually, I feel like. Okay, so we got this deck, right? Once we create the order, like we said, we're gonna create a queue. So for let's see, for key in order dict.keys, we're actually going to queue.append key, right? And then now we're going to go through everything in, so we're going to go through while queue cur letter is equal to queue.pop left. And then when we pop left, we're going to just simply, we also need to keep track of a res variable. Res, if s dict, if cur letter in s dict, then we will say res plus equal to s dict. of cur letter, which should be however many, right? And by this point, we'll have all of the, we should have whatever order respected for the output. And then now we gotta actually also consider, the thing is, right? I think we can actually just delete. I think we can actually delete stict of cur letter, because once we delete it, by the end of all of this, we can once again, right? If for key val in stict dot items, if we do even have items, we can simply res plus equals what is this? How do I do this? Well, actually, technically, for underscore in range of stict, no, this is, hold on, stict of cur letter, we're technically supposed to loop this many times, and then we just res append cur letter like this. I don't know if this is jank, but this is the way I'm thinking about doing it. And then res plus equals again, we do the same thing for underscore in range stict of cur of key, or actually range of val, and then res plus equals key, and then we can just return res. Oh my god, first try, I'm the best. But low key, I don't know if it's really that optimal. Oh my god, I didn't even need to like look at an answer key and I solved it. I feel like my solution's a bit jank, I can't lie. Or maybe not. Maybe it is optimal. Maybe not. Alright, let's see how the smart guys do it.
This your bag, sir?
What gave it away?
Oh, you go! I found a claim for my call.
Hello, and welcome back to the Cracking Fan YouTube channel. Today we're going to be solving Leetcode problem 791, custom sort string. Let's read the question prompt. You are given two strings, order and s. All the words of order are unique, and we're
I don't know what the
sorting
question is.
and then G, F, D, or F, D, G. It doesn't matter for these last three because they're not in order. We only care about order, over order, and build our string as we go. So we're going to go, from left to right.
Impressive, yes, impressive.
Since our order string, we still haven't rearranged, s. So what we need to do is actually, when we're going over order, when we see, okay, do we have these C's, we add it to our string builder. We're actually then going to remove that key. So we remove the C after we added the C's. And then we have the B, we add it to our string builder, then we remove the B key, and we do the same for A. So that means that at the end, whatever is left in our dictionary here is going to be, characters that were not in our order dictionary. Now what we can do, like I said, is just go through the remainder of the dictionary and then just
That's literally what I did.
add each character and its count to our string builder here, because at this point the order doesn't matter. They weren't in our order string, so that means we can return them in any permutation that we want. And this is how we're going to make sure that we don't accidentally double count it by going over the dictionary again. So to summarize, the first thing we're going to do is we're going to build our count dictionary here, which is going to have for every character in S, we're going to have the count of it.
Oh, he does an array, I think. Interesting. I guess that kind of unjanks this kind of logic. Because this logic is low-key a little jank, I feel.
Then what we're going to do is we're going to iterate from left to right of our order here, and we're going to look, okay, for every character, is it in our count dictionary? If it is, we're going to add that character however many times it shows up in our dictionary. Then we're going to delete it from our dictionary, and we're going to go on to the next character and do the same thing. So C, then B, then A. And at this point, whatever is left in our dictionary are going to be characters that weren't written in order, and that means that at this point we can just add them to our string builder for however many counts they have, because order doesn't matter at this point. We've already satisfied the order by iterating over it entirely. So that's gonna be how we're gonna solve this problem. Let's go to the code editor and actually write the code and see how we're gonna implement this. Okay, so now we're in the editor, let's write the code. Remember that the first equal to a list, and we want to remember iterate over each character in the order. So we're gonna say for char.
But he didn't need a queue, though. How?
We're gonna then say if the current character is in S counts, then remember that we need to add it to our string builder however many times it occurs. So we're gonna say res.
Oh my god, I'm so dumb. Oh my god. Wait, I'm so dumb. Why did I need to create a queue? I didn't need to create a queue. I just realized I can just go in the order of this string. Am I brain dead? Wait. I might actually be stupid. If an interviewer saw this, I'd feel like I'm dumb. Oh my god. That is just so dumb though. All I needed to do... Oh my god, I'm so dumb. I didn't need any of this. I don't need any of this queue. We can just literally just have a pointer, I guess, to order low key. So I is equal to 0. And then while I is less than the length of order. Right? It is not even q.pop left. It's order of I. Anything else with the queue? This should still solve it. Oh wait, I need to increment the pointer though. Besides that though. Oh, and this. Taking the above back. Look, it still works. Okay. Okay, wow. I don't know why I thought I needed a queue, but I mean still, even though my solution was jank, it still worked. I mean, it's a little bit of extra work that I need to do, but still, like, it did work. So, like, I still know what I'm talking about. You know what I mean? Like, I made the question harder than it needed to be, and I still got it right. But interesting. Next time, yeah. Okay. Yeah, that's right. I think I was just tripped up at the fact that, like, I don't know why I thought I needed a queue. This question's easier than I thought. I overestimated the difficulty.
Stock code sound red. When you say string build.
So this guy uses an array. Yeah. Yeah, he uses like array manipulation. Let me ask ChatGPT what's better. Is this better, or is it better to create an array first and then do a join at the end? Strings are immutable, so every time you do it, it creates a new string object, which is inefficient in the loop. Frick. Okay. So I guess whenever I can, I should probably try to do arrays. I think arrays are generally better. Okay, so I'm gonna make res like this, and then we don't need this then. Well, could I do this instead? I feel like this is low-key still kind of troll. And then CH times... Okay, so you could just do that. Oh, that's nice. That's easy. Okay, so I don't need this. Times stict. So I could just do it like this. Oh, whoops. What? Okay, what is wrong with this? Key times val. Oh, fudge. I didn't need this. My bad. Okay. It's way simpler than that, I guess. Okay. So, I guess if I were to come back to this question again, the custom sort string. Okay. We have an order, right? We're given an order. This is the order they want us to respect. And this is also, all the characters are unique and they were sorted in some custom order previously, whatever, sure. We have some order. And now we have an S. We want to basically have all the counts of S. And then if we have A, so we're going to look for C, right? How many C's do we have? We have 1. We're just going to append 1, then 1B, then 1A, and then everything else after we just append after. So I'll have res as an array because arrays are better than doing string manipulation if we can. By the end of all of this, we can just simply return the join of res, right? And so we're going to have the s count or s dict equal to the counter of s, and let's just have a counter for I. So while I is greater than or less than the length of order, we can traverse through the order, right? And let's go through order, right? So if order of I in sdict, then that means it's valid, right? And we have a matching character that we can add to our res. So res.append order of I times the value of whatever's in sdict of order of I, which I guess maybe we should be a little bit cleaner, and instead of just writing all this like order of I nonsense, let's just store order of I as the char is equal to order of I, right? So if the character is in the dict, and this char will be multiplied by the value of the key in sdict, right? And then at this point, we're actually also going to need to delete that key value pair. So delete sdict of char because we've added it to the dictionary. And then by the end of all of this, we're gonna have to go through for key val in sdict. We're gonna see if there's any remaining ones, right? And then we're just gonna append this after res.append key times val. Then boom. I forgot to update the I pointer. God damn it. I'm bad. Oh shoot, it should be sdict.items. Yep. Okay, this makes sense. This makes sense. This question is not too bad. I feel like this question I can intuitively understand. And those are medium questions, so chilling. create a dict for the string. And delete if we find it, if it once we that from the dict, once we add it to res, do a final check if there's any other remaining characters. It's not too bad. Okay. Alright. Custom sort string. K closest points to origin. I technically know this question, but I think this question's actually not bad either. Okay, so in this question, you're given an array of points where points of I is x1, y1 represents a point on the xy plane, and an integer k return the k closest points. Anything with regards to like give me the k number of things, we want to keep it with a heap. Now the thing is, how are we going to maintain this heap? Do we want a min heap or a max heap? I think, let's say, let's see the examples here. K closest means we want the smallest values, right? So I think a min heap should suffice. But the thing is, like, if we pop it, it's gonna pop the min heap, the smallest value, which is actually what we don't want, right? So do we actually want a max heap here? I don't want to cheat though. I want to like test my understanding of this topic. The thing is, like, let's say, okay, let's just calculate the distance for this, right? Technically, the formula is x1 minus x2 squared plus y1 minus y2 squared. However, we're always basing it off the origin, which is 0, 0. So it's actually just x1 squared plus y1 squared. The square root is also technically irrelevant, because if we're just comparing between distances of others, we really only care about the x squared plus y squared value. So I guess in this case, 1 squared plus 3 squared is 10, and the other one is 4. So in this case, right, if we had a heap, we'd add the 10 first. We'd pop the smallest element, which is 10 at this moment, but then it goes to 4. Well, I guess we'd actually add 10 and then 4. But the thing is, like, we'd add the 4 and 10. And if it was a min heap, we'd actually pop the 4, which is wrong, right? So I'm not sure how I feel about a min heap. I think we actually go with a max heap here. So what we'll do instead to imitate, I guess, a max heap, we'll actually just create a negative value for these. So like this 4, 10 will actually be a -4, -10. Because in this case, because -10 is smaller than -4, the order would be like this. And now when we do a pop for the heap, we'd actually remove the 10, which means the 4 would remain, and then I guess by the end of the conversion, like, we revert it back to a positive number. Well, I guess we don't even need to care about converting this value, because all we're concerned about is returning the coordinates. So we'll just keep that in mind. We'll store it as a tuple, of course. So we're gonna do like, we're gonna have to convert the distance to numbers to keep only the closest points. All right, so the first thing we're going to need to do is create a temporary kind of array, I guess, to build like a tuple that will contain the distance and the x and the y coordinates for our heap. And so we're going to call this maybe dist or tupes or dist tupes, or I don't know what to call this. I'll just call it temp, whatever, I don't care. So it's going to be a temporary variable, which is going to now go through all of the xy endpoints, because every point has 2 values within each array or subarray, and dist is equal to x squared plus y squared. And we can temp dot append a tuple, which is actually the negative dist x y, right? And then this should generate our heap. And then at this point we can actually, as we do this though, we can actually just append to our heap. So instead of doing this, I'll just do a heap q dot heap push of this, right? And as we do, well, yeah, I think this is fine, right? And if at any point, if the length of temp is greater than k, we're going to need to heap, well, hold on. I mean, is there a chance that we potentially pop something that we shouldn't have popped? I don't know, actually. I guess I'll find out. I guess my current thinking is that we can do this as we go, but I'm wondering if we need to go through all of them first and then append to our heap. Thing is that if we do it as we go, I don't think it would matter. I think this would still work. I think it should still work. So we'll do a heap q dot heap pop. And this way, like, we're maintaining a heap of size k, which is nice, instead of just, you know, the heap would otherwise be the length of the points, which could be way longer. And then in this case, once we've created our heap, we'll still have enough things in the heap, right? So for there's a dist xy in temp or temp in temp. Res dot append xy turn res. Yes. Let's go. Let's go. Let's go. Let's go. I don't even think I solved it that way before. Yeah, I think the old way I did it was actually less optimal. Because I go through everything and I just append to the array and then I heapify it and then I'll just, yeah, this is not efficient. Not as efficient as, because like if I were to run this solution, I think it should run slower in theory. Yeah, it's slower. I'm pretty sure this is like, and the thing is like, I'm pretty sure I need to have a negative distance. But how did I do it with a positive distance? This makes no sense. Oh, it's because I let everything in the array. So yeah, when I pop at the, like when I pop it, it will technically just give me the smallest values anyways. But this is like, this is smarter though. This is more efficient. I see. I feel like I'm learning. I understand. Like it makes more sense. It's more efficient. Okay. All right. Next question is a hard question. It's a hard question, but we'll see. Maybe it's not too hard. Heap question or heap min heap with negative distance and keep heap of size k. Pop. Heap. Add the heap to a res in the format they want. How many questions have we done so far? 33? Yo, there's no way I'm making it to the end. I feel like by the end of the interview, there's no way. I mean, at least I don't know. There's no way. There's no way I'll get to all of it. Okay. Holy frick. We're given an n by n binary matrix. You're allowed to change at most 1 0 to be a 1. Return the size of the largest island in grid after applying this operation. Oh my god. Okay, so you're telling me like if I had a 1 0 and then I had a 0 1. Obviously changing one of these will make the area 3. But like by themselves it's only 1. So like how are you supposed to figure out I guess you could check if like I just want to see the comment section real quick. I like seeing the comment section and seeing how solving this question is better than having okay. It's a square. The thing is, like, I was thinking, technically the only way to, like, merge an island is to check diagonally. if there is one, right? Because like, how else are you supposed to know that there is an island out there? Like traditionally, we're only checking if it, you know, you can only check left and right or up and down. But then past that, if you check diagonally, you can see that there is another island. And if this problem was bigger, you'd see that you could technically combine the two plus one. But I don't know if that's the right approach. I need a hint. And there's no hints? Okay, I guess. Alright. That's fine, I guess. I mean, I can't really think of any other like intuition behind it. It's either, so there's like two cases, right? It's either we just add to the biggest island. That's the thing, right? It's either you just, two scenarios, two cases. You either add to the biggest island, or there's a merge possible, right? Because you could have two medium-sized islands, and there could be one island that's like massive by itself, but there could be like two islands that are like on the cliff, on the merge, on the verge of merging together. And if you just merge those two together, then they will create an even bigger island, right? So then it would just be those two medium, like medium plus medium plus one is now the merged island. Is that the intuition? I don't know. That could be. I don't really know how I would even code the diagonal portion of it. I feel like that'd just be a lot of work. Maybe. You add to the biggest island. I don't know. I don't think I'm going to waste too much time though. I want to see what they say. It's a 30-minute video.
Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve the problem making a large island. So this is a hard problem, but I will say that for a hard problem, I think this one is somewhat reasonable. I'm not saying it's easy, but there are some hard problems where you have no idea how you would come up with a solution, and I think this is not one of those. I think
I can't even really, I mean, I don't know if I came up with a solution. I don't know if it's valid.
you can at least get close to arriving at the solution like on your own. I'll be kind of doing my best to like walk you through that process. I'll also mention that I'll briefly be showing you two solutions. The first solution I guess I'll show you is mine, like the code for it. I won't be coding it up, I'll just show it to you. The reason for that is because my solution is actually more complicated than it needs to be, and there actually is a other solution that I'll be coding up for you, which I'll call the clean solution. And these are actually both just as efficient as each other in terms of big O runtime. Even in terms of real runtime, they're about the same. but the second one is just much more simple. And I think sometimes when you figure out like a solution and you know it's going to work and you know it's optimal in terms of video runtime, you can kind of go down that rabbit hole and forget to kind of think that, maybe there's actually an easier way to implement this. And I think that's the mistake that I made. I knew that my solution worked. I thought, okay, it's a hard problem, so maybe the code just needs to be really complicated. But actually, the code could be made like 15 lines shorter by coding it up the clean way. And once I realized the trick behind the clean solution, which is basically just to invert my thought process from like my original solution, I felt like kind of dumb. I was like, oh, damn, it's just that simple. So that's kind of what I'll be walking you through as well. So the idea behind this problem is that we are actually given a square matrix. I don't know why exactly it's square this time, but it is. And it's going to be a binary matrix. So you can think of it as 1 represents land and 0 represents water. The reason I say that, they don't really mention that in the problem description. The reason I say that is because we are trying to form the largest island that we can. Islands are made up of 1, and they are connected in all 4 directions. So left, right, up, down. So you can see this is one island and this is one island over here. They are unfortunately not connected to each other because we cannot connect things diagonally like this. But in this problem, we are allowed to change at most 1 0 into a 1. So what we could do is change this into a 1, and then we form this island here of size 3. Or we could change this into a 1 and form this island of size 3. So the solution for this first example is going to be 3. We do that by taking this island, which had an area of 1, this island, which had an area of 1, and then by changing this water into land, we also get an area of 1, so we can add all of these together. Now let's start going through some examples to consider some edge cases as well as build intuition for this problem. First of all, they tell us we could change at most 1 0 into a 1. What if we had an example like this one where it's just 1 and the area is 1 and there's nothing for us to change? Well, then the return value would be 1. We have this island. We weren't able to change anything from 0 to 1. And that's perfectly fine. I think this third example illustrates the same thing. What if we had a 4x4 where everything is 1? We can't change anything. The area of the island is already 4. That's the max area of the island. So that's what we can return. Consider maybe a different example where we had something like this. I'm not filling in all the values for this grid, but suppose that we had an island over here, which is of size 3. We have an island over here, which is of size 3. And everything else in between here is water. Well, you could change any of the cells into land, but we're never going to be able to connect multiple islands together by doing that because they're just too far away from each other. The closest we could do is change this into a 1, which would increase the size of this island into 4, or doing that down here as well. Now, in this example up above, we took 2 islands that were of size 1 and joined them together, but we could actually take even larger islands and join them together. I think this is a pretty simple example of doing that. Suppose we have 1 1 over here, 1 1 over here, and we have a 0 over here. By changing this into a 1, we take the size of this island, which is 2, the size of this island, which is 2, and now we connect them together. You can think of this as like a bridge that connects these together, and the size of that bridge is relevant to the
That is what I said. That's exactly what I said.
total calculation. So we do 2 plus 1
Peanut butter pretzels.
plus 2, we get a total area of 5 for the largest island that we could create. But now you might be thinking, well, we're just going to look for the 2 largest islands that we could connect together. And that's what I initially thought. But actually, it's possible that we could connect more than 2 islands.
That's true. It could be more than 2.
Actually connect up to 4 islands together. Let me show you a
Yeah, I mean, that makes sense because you have to check all the diagonals.
pretty simple example of that. Again, this is a pretty rough drawing, but I think you probably will get the idea. So I'm gonna have zeros filled in for all these quadrants and here as well. So what I have is an island over here, an island over here, an island over here, and an island down here.
Actually, it doesn't have to be diagonals, I guess.
0 over here. If I flip that 0 into a 1, I look above me. I just connected this to an island above me. And I just did the same with an island to the right of me and below me and to the left. So I took a 2 over here and a 2 over here and a 2 over here and a 2 over here, and I connected them to this 1 at the center. So that gives me a calculation of 2 plus 2 plus 2, and all those plus 1. So that's going to be a total of 9. So now the problem is getting a bit more interesting. You may not necessarily know what the solution is at this point, but at least we're building a little bit of the intuition by going through some examples. So now I'm going to walk you through sort of what the solution is at a high level. I could explain to you what my original thought process was, but I'm actually not going to start with that because I think mine, since it resulted in the slightly more complicated solution, I think you'll probably find the other thought process more simple. So that's what I'm going to start with. So one very brute force way to tackle this problem, let's just consider this example here that's in front of us. One very brute force way to tackle it would be to take every single water cell that is available to us, consider it, and consider flipping it to a 1. And then for that cell, look above, look to the left, look to the right, and look below. If there's a land cell in any of those locations, then we want to get the area of each of those islands that are adjacent to the cell that we just flipped. So obviously that could be done relatively simply, I think with a DFS or a BFS. If you're watching this video, you probably know how to implement those. And if you don't, I think this problem, since it's a hard one, is probably beyond you. You might want to consider checking out like Leetcode.io or some other resources to learn these things. But we could do that, and that would be one brute force way to do it. But one thing you might realize is that, let's say for example here, we flip this, we turn this into a 1. We're gonna look to the left, there's nothing there. Look above, there's just water. We're gonna look to the right, that's nice. There's an island over here. So what we're gonna do is get the area of the island. We're gonna end up traversing the entire island. We're gonna look below and do the same thing, get the area of the island and traverse. Okay, so the calculation we get in this case is gonna be 2 plus 1 from the cell that we flipped. So the area was 5. Now we can try it in a bunch of different places. We can try it here as well. Try it for every single water cell. We'll do this. We'll end up getting the area of this island. We'll end up getting the area of this island again. So you
Guys, repeated work though. I'm assuming there's some way to like memorize all the past islands that we have visited.
see That's the repeated work.
Yep.
Wouldn't it be nice if we already had the area of every single island beforehand? We pre-compute that, and it's not that difficult to do. That will just be an n-squared operation where in the worst case we end up visiting every cell in the grid. So if we pre-compute the area, then doing this flipping algorithm is actually going to be very, very efficient. Because what we'll do in that case is, suppose we're here, we will look below and see that there is a land cell. We can just easily get the area of that entire island without having to retraverse it. And same thing in any direction. So that is the intuition for the clean solution. Maybe you don't care about like what my solution is. If that's the case, you could probably like skip the next minute or two. I'll just briefly walk you through like my solution, like the intuition of that, because it's very, very similar. It's just slightly different. My solution is this. I do the same thing. I pre-compute the area of every island, but the second part of my algorithm, rather than going cell by cell and trying to flip it and then looking in all 4 directions, my solution was to do a BFS from each island, because this was my intuition. Okay, if I do a BFS, let's say from this island, I don't think it has to be a BFS. Maybe you could have done it with a BFS. I just think it was easier to code up iteratively, so that's why I did a BFS. But suppose you take this island here and you traverse it. You go from this cell and then you get to this cell, and then from this island, you try to flip any adjacent 0. So it's kind of the opposite of the other solution I was showing you. So we're gonna look up here. There's a 0. What would happen if we flip this 0 into a 1? Would we have connected anything in any of the 4 directions? Yes, there's an island over here. So if we were to flip this into a 1, then we would have connected this island and gotten an area of 5. And then try from every adjacent spot. Okay, what about this guy? If we flip that into a 1, well, we'll just get an area of 3, nothing new. And eventually we'll also look over here. What if I flip this guy? Do I get anything new? Well, this is something we already had, but down here I get the area of 2. To the right I get the area of 2, and up above I get the area of 2. So conceptually, it's a very similar solution. It just happens to be that this one is a pain in the ass to code up, especially like this part of the code. So that's why I'm going to be sticking with the other solution in terms of implementation. But even knowing what I explained to you so far, it's not trivial to implement this. The number one question you'll probably have when you try to implement the solution where we try to take each 0 and flip it into a 1 and then look in the 4 adjacent directions is, well, how exactly are you going to store the area of each island? Assuming we pre-computed the area of every single island, how exactly would we store it? Because we need to store it such that if I'm over here, I look down and I see, okay, there's a cell over here, and it happens to be a 1. Well, what's the area of the island belonging to that 1? Or the area of the island that this 1 belongs to? Well, that's a question of how exactly do we store it. Now you might think, well, okay, maybe I could store it based on the position. Maybe I could map the row, column, index, the position of it, the row and the column, and I can map it to somehow like the island.
Yeah, that is true. I was wondering how you store it, because the area is based on a bunch of points. So it's like, did I just close the video? What just happened?
Hello, and welcome back to the craft.
What just happened? How did I lose the video?
Happens to be a 1. Well, what's the area of the island belonging to that 1? Or the area of the island that this 1 belongs to? Well, that's a question of how exactly do we store it. Now you might think, well, okay, maybe I could store it based on the position. Maybe I could map the row, column, index, the position of it, the row and the column, and I could map it to somehow like the island, and that would give me the island area. This is more or less what we're gonna do. But before I show you exactly how we're going to do that, do you also agree with me this? We need to uniquely identify an island. Why exactly is that? Let me show you with a brief example. Suppose I had an island like this one, and let's assume everything else is water. If I take the 0 that's over here and flip it into a 1, I might think I'm a genius. I might look to the left and see, okay, there's nothing there, there's water over there. But I might look above and I might see that, okay, we found an island, and the area of that island happens to be 5. That's awesome. And then I look below and I say, okay, the area of that island also happens to be 5. But it's not a different island. It's the exact same island. By adding a 1 here, I'm not connecting any of these together. And by looking to the right, I'll see the same thing. It's an island of area 5. I will overcalculate the area of the island that I just formed. I will get an area of 5 plus 5 plus 5 plus 1, which will give me 16, but that's not what I did. So when I look up above, I need to see that this is an island, and I need to know which island it is. So then when I look down, I see that, okay, that's the island I've already seen before. I don't need to re-add the area of that island. So that's why we need to be able to uniquely identify each island. And so consider the mapping that I wrote down below over here. We need to somehow map each position to which island it belongs to, and then which island it belongs to, we need to somehow map it to the area of that island. There are multiple ways to do this, but the easiest that you probably can think of is we literally have a matrix over here. The row column could be used itself. This is a 1, but we could have changed it to a different value. We could have changed it to whatever label, unique label that we prescribe to the island. So we know that in this matrix, we're only dealing with 0s and 1s, so we can use any value that is greater than 1. So starting at 2, we could start using those as the labels to differentiate each island. Let me show you what I mean with an example. Consider this matrix over here. I have two islands. This is an island and this is an island. When I get the area of this island, I could change the value of each of these into a 2. So then I can differentiate this from any other island. And when I traverse this island, I can change each value to a 3. So now I can easily differentiate any cell that belongs to this island from any cell that belongs to this island. Now, obviously that involves overwriting the input matrix, but to get around that, if we really needed to, if your interviewer doesn't allow this, you could just create a copy of the input matrix. I don't think that's a big deal. It's not going to change the overall space complexity of the solution anyway. So now that I have a label for each cell in the island, I can take the island, so in this example, a 2, and I can map it to the area, which is 4. I can take a 3, which is the label for that island, and map it to the area, which is 5. Probably we can just use a hash map to do this mapping. So basically, to summarize, we kind of realized we need to do something like this. I took this and just put it into the matrix, so then all that's left for us is this part, map each island to the area of that island. So this part that I just showed you, this is the part where we do the pre-computation. That's phase 1 of the algorithm. Phase 2 isn't too bad, so I'll just go ahead and show it to you now. Phase 2 of the algorithm is basically like playing Connect 4, not literally, but in the sense that we take a 0, we flip it into a 1, and then we connect in the 4 adjacent directions. So not like the board game Connect 4, but a different kind of Connect 4. So to do a brief dry run, let's say we tried flipping this one into a 1. What we would do is look in the 4 directions. We're out of bounds here. To the right, there's a 0. Below, there's nothing. To the left, we see a value. That value is 2. What does that tell us? Well, we have a hash map already that gives us the area of each island. That hash map would look like this. 2 is mapped to 4. 3 is mapped to 5. So we get the area of that island, and the area is 4. We will add it to what we have, which is 1. So the total area that we could form is an island like this one, which is 5. So we're going to keep repeating this process until we find the maximum island that we could form. And by the way, when we get to a position like here, we're going to look up above and see that there's a 3. We're going to get the area of that island, which is 5.
Island question? Yeah. Making a large island, though.
At that point, we are going to add this island to our visit hash set, or at least some kind of data structure to know that we've already seen that island before. You technically don't need this to be a hash set. You probably could use an array as well, because we know the size of this is never going to be greater than 4, because we're only looking in up to 4 different directions. We could only have up to 4 adjacent islands next to us anyway. So that's why we're doing it that way. We're only marking this island as visited while we are at this cell. When we move to this cell over here, this island is no longer visited. The solution for this problem is going to be, I think, when we flip this one or this one, because if I flip this one into a 1, nothing up above, nothing below, but to the right, I have an island that's not visited, area 5. To the left, I have an island, area 4. So I can take 4 plus 1 plus 5, which gives me 10. Overall time complexity of the solution is going to be n squared, same with the memory complexity. That'll make more sense when I code it up. So you can see when I was coding it up, I actually had a couple wrong submissions, but this was the first submission that I had, and that's the intuition, whatever. And so most of this code is the same. You probably don't actually care about this code, which is fine.
There is no way a meta engineer will ask me this question. There is no way. There is no way. I refuse to believe it. Expecting a candidate to code this in 18 minutes and even come with the intuition in 18 minutes. Are you kidding me?
Fine, but you can
That is disgusting. There's no way.
see here, this behemoth, the BFS, that ended up being the most
Let me see. But Meta asked it 30 times. Apparently.
complicated part. And once you simplify it, you can get a solution that is much more clean by replacing it with this connect function, which is what I'm going to show you right now. And look how much shorter the code is for that. So I'm going to start out with some very trivial boilerplate. We're just getting the dimension of the grid. We know it's a square matrix, so that's why I just have n here. And I have a little helper function given a couple coordinates. I'm going to detect if the coordinates are out of bounds. We're going to be needing this in a few places, so that's why I just have it here. So for phase 1, we are going to pre-compute the areas. So I'm going to have a hash map here. I don't think I actually need to make it a default dict. I needed to in my BFS solution, but I don't think I will in this one. But anyways, this is going to take an island label and it's going to map it to the size of that island. The label is going to start at 2, so I'm just going to have a variable here. And what we're going to do is now just traverse over every single possible position. So for R in range N, for column in range N, if we encounter a cell that is non-zero, what we are going to do is get the area of that island. I'm going to do that with a simple DFS. I think you could also do it with a BFS if you want to, but I'm going to pass in the coordinates and I'm going to pass in the label that we now want to give this island. This DFS is going to overwrite all of the cells in that island and change them to this label. And it's going to return the size of the island. So I can just store the size like this now, mapping the label to the size. And then after that, it's very important that you increment the label so that we do not reuse the same label for multiple islands. So let's increment this by 1. Now, you might be realizing what happens if we encountered a cell that was not 1, but maybe was 2 or 3. Well, that would have been an area of an island that's already been visited. We do not want to revisit the same island multiple times. I guess we could get around that by having a visit hash set, but we actually don't even need to do that. We're already using the input space and overwriting it. We're pretty much using that as our visit hash set. So we can just say, as long as this is equal to 1 and it's not equal to 0 and it's not equal to 2 and it's not equal to 3, then we are going to traverse this island that hasn't already been visited.
When your kid is hurting and there's nothing you can do about it.
I'm so tired of seeing that ad. I'm sorry. I don't know if that's insensitive, but I'm so tired of seeing that ad.
That's out of the way. Let's actually implement the DFS. It's not going to be super difficult. You've probably seen this several times, but there's just a couple small changes. So one, I'm going to check if we're out of bounds. In that case, we are going to return 0 if out of bounds from these coordinates, or if the grid is water, then we want to skip it. Or if maybe this position has already been visited. If it has, that means we've given it the label. So if this is equal to the label, then we also want to skip. So in those cases, we could return 0. Otherwise, what we would do is give that position this label. Now, one small way to simplify this is just to say, if this is not equal to 1, that's when we don't want to continue, because that accounts for the fact that this could be 0, or it could have been already visited. So basically, we're saying if this is unvisited, then traverse it. And it's also not water, of course. So after that, we get into the part where we actually want to compute the size of the island. Given that we are at a cell that is technically land, we can start our size at 1, and then in the 4 neighboring directions, which I'm going to do like this, r plus 1 column, r minus 1 column, r column plus 1, r column minus 1. And then we go through the 4 adjacent coordinates, we unpack the coordinates like this, and we want to run a DFS in all 4 directions, we can do that like this, and also don't forget to pass in the label. And what this should do is return the area of the portion that is in those directions that hasn't been visited yet, so we can take that area, add it to our current size, and then return that. So we're not really doing anything super crazy other than just overwriting the input matrix. So believe it or not, we're almost done now. The rest of the code is going to look something like this. We want to try flipping every water cell. So what we're going to do is go over all the coordinates once again. If we encounter a cell that is water, so if it's equal to 0, then we want to try doing connect. So we're going to implement a helper function up above, which is going to help us to do that. I'm going to call it connect. I think it just needs to take a couple coordinates. And so this connect is going to return to me the max area that we could form by flipping this cell into land and then connecting it to any of the 4 adjacent islands that might be next to it. And so what we ultimately want to do is maximize the result of all of these. So we could have a result here, and then the result could be maximized like this. And after that, what we would do is just return the result. So one thing I want to mention is that this is actually not the correct initial value to give the result, because consider this. What if we had a matrix that was like all 1s? We have a 2x2 matrix, let's say, like this. Well, we're iterating over this. We're never going to see a water cell that we could flip. So we literally never flip any of the water cells. So this code would end up returning 0 for this example over here. But we know that we actually do have an island, and the area of that island happened to be 4. The better way to initialize this would be to say this. It's the max of the size dot values. So size, remember, is the hash map that we had up above, which stores the size of every single island, and we're just getting the max area of an island from that. But then consider this example where we have maybe a 2x2 matrix, which is all zeros. Well, in that case, this is actually going to be empty, and if we try to take the max of an empty iterable, we're actually going to get an error. So the best way to initialize this, at least the one that I did, is this. It'll be 0 if size is empty, so if not size. Otherwise, it'll be the max value that we have in that array. I guess what you could have done is just initialize the result up above somewhere. We could have initialized the result over here, and then at every single step, we could have maximized the result by just taking whatever the area was that was returned to us, but I didn't do it that way. You could do it that way if you prefer. Now we're almost done. Just have to implement this connect. It's not going to be too bad. We're going to have our 4 neighbors, and I'm just going to copy and paste them from up above, actually. So let me do that.
This code is so
These are the 4
long.
adjacent cells to this water that we are flipping. So what we're trying to do is go through those neighbors as long as that neighbor is not out of bounds. And the way I'm going to code this up is by saying this. If the grid at that, or the value at that position, which is the label, is not in my visit hash set, which I'm going to declare up here. Visit is going to be a hash set. So this means it's an adjacent island that hasn't been visited. Then I'm going to do this. I'm going to say add to the result size of that island. The label of the island is this. So I'm going to copy that and pass that in as the key for our size hash map. If I do that, I'm also going to mark that as visited. So I'm going to add that label to the visit hash.
Oh my god, I'm low-key just like not listening.
I traded my broken phone for Galaxy S25 Plus on T-Mobile, and without we splurged on a
Hello, and welcome back to the Cracking Thing YouTube channel. Today we're going to be solving Leetcode problem 827, making a large island. Before we get into this problem, I just want to say, if you haven't watched my videos on either max area of an island or number of islands, please go watch those videos. We're going to be using some of the same techniques to solve this question that we used to solve that one. If you don't know how to solve those, you definitely won't know how to solve this one. So please go back and watch those first, because they lay the foundation of how to solve this problem. This problem is labeled hard on Leetcode, and you're going to need some of the principles that we learned in the mediums to use the same topic to actually solve this one. So that being said, let's get into the question problem. You're given an n by n binary matrix grid. You're allowed to change at most 1 0 to be a 1. Return the size of the largest island in the grid after applying this operation. An island is a 4-directionally connected group of ones. So for example, if we have this island here, which is, so we have this grid here, right? And we can see that there's one island currently, and it's the island, with these 2 tiles. So what's the largest area? If we could flip 1 0 to a 1. Well, we can see that if we flip either of the zeros, we get an island of size 3, right? We made this a 1, then we get size 3. So the answer here is 3. And it seems quite simple how to do this if you're looking at the grid, but how to do this programmatically is a little bit tricky. So the naive solution would be to simply go through all the grid. Every time you see a 0, transform it to a 1, and then kick off a depth first search in all 4 directions to basically count the number of islands adjacent to it, sort of how we did max area of an island, and then add that up and then keep a result going as we go. The problem with this solution, though, is that you're going to end up recomputing the areas for multiple islands. For example, if you were to do this here, you compute the area of this island, which is here, but then when you get here, you'd be recomputing that. So unless you did some sort of memoization, you would actually essentially end up repeating a lot of calculations, which we don't want to do. What we want to do is actually pre-compute the areas of each island. And the thing is, we don't want to count an island multiple times, right? Because if we say, okay, well, if we're at this 0 here and we flip it to a 1, and we go to the left, and then our DFS is going to go in all 4 directions, we will accidentally count this island twice, right? We'll go here, and it's going to count this entire island if we do a DFS. But then when we go down as part of our original DFS, we'll get here, and that will DFS into the top one, and we'll actually count it twice. So we have to have some mechanism to actually count our islands in a unique way. So what we're going to do for this problem is actually, we're going to do one iteration through our entire grid just to figure out the distinct number of islands. And what I mean by this is, let's say we have a bigger grid here, and we'll kind of just draw it out. And let's say we have an island up here, have some 0, we have an island here. So this is an island, this is an island, and then there's an island over here, right? These are all distinct islands. I'm going to change my color. So this is going to be an island, this is going to be an island, and this is going to be an island. What we want to do when we go through our first iteration here is actually to change all of these ones to whatever the island ID is. And we're going to start the island ID at 2. And the reason we want to start at 2 is that way we don't end up overwriting characters that we already used. We can use 2, or we can use something like -1 and then go to like -2. That way we make sure that we don't actually end up writing a value that's already in the grid. So for example, let's say we started with -1 is our island ID. So we start here at the top left, and we see that this is an island because it's a 1. So we're going to set all of the tiles that this island touches to be equal to -1. And so we're going to set this equal to -1. And now that our DFS finishes here and we found this island, we can then move on to island ID -2. So the next island we see, we're going to set all of the values of that island to be -2. So we keep going, traversing over our grid to find all the islands, and we get to this one now, right? So we're going to set its value to -2, and again, we're going to try to kick off our DFS in all 4 directions. But we can see that there's actually no more islands here. So that means that this is the only one in the island, which ID -2. And what we're going to do is we're going to have a dictionary which maps the island ID to the actual area of the island. So this one was area 2. We have area of island with ID -2, and area is 1. And then we'll see that now our ID is going to be -3, and we're going to have this island of area 2. So we're going to set these equal to -3, -3, so now we have -3 and 2. So the reason that we want to do this is, I guess, when we go through for a second time and we get to a 0, now we don't actually have to DFS into our surrounding tiles to figure out the area of those islands. We can simply say, okay, well, where we started at 0, we're going to flip it into a 1, but we need to figure out the area of the islands that would be formed if this was a 1. So what we need to do is basically, is there an island to the left of me? If yes, I want to add its area to my current area, which is 1. Is there an island to the top of me? If yes, and I haven't seen that island, because it could be the case that this is also, -1. So that's why we have these sets -1. So we can maintain a set of all the islands that we've taken points from to make sure that we don't have duplicates, because we don't want to count the area of an island multiple times. So for example, when we go left, we want to take the area of islands with an ID of -1, then we go to the right, we can see there's an island with -2 IDs, so we get its area, which is 1, and then obviously -1 is 2. When we go down, we can see there's no island here, and we go up, obviously it's outside the grid, so that's not valid. So we want to add the area that we get from flipping this 0 to a 1, so it's going to be 1, plus the area of the island -1, which is next to our point that we just flipped, so we add 2, and the area of the island with ID -2, which was to the right of our current island. So that means our new island would be this big one here that we formed, and it's of ID 4. And this is going to enable us to basically not have to do the DFS each time, calculate the area, because we've pre-calculated it, we've stored it here, and we can essentially just reuse the computation. But remember, we have to keep track of the islands that are next to us with the set. We don't want to accidentally count an island multiple times. in the case that it actually has, like for example, if this tile here was -1, then we would count this as the area here, but this already includes it. And if we went down, we accidentally double count it. So that's why we want the set here to make sure we only count islands one time. So this drawing is getting pretty much into like a bowl of spaghetti here. It's getting really messy. I think at this point what I want to do is actually transition into the code editor, where we're going to type this out, go through line by line, and hopefully it should be a whole lot more clear, because it is a little bit confusing to look at the example, especially with all of the kind of squiggles going on. So let's stop this here. Let's go to the code editor and write this out. It's really not that bad of a problem. It is quite a bit of code, but it's not really that complicated. You should know how to do this from those previous problems that I told you should know how to solve for finding this one. Anyway, that's enough rambling. For real, let's go to the code editor. We're in the code editor. Let's code this up. Remember that I told you that we want to have an island ID, which is going to keep track of each individual island, so that way we can overwrite its value in the grid, and that way when we go back for a second time, we can actually know which island we're working on in a really good way. So let's say that self.island ID is going to start at -1. So we don't want any flashes with values that are already in the grid, which are 0 and 1. So obviously we don't want to start at 0, we don't want to start at 1, because that's going to make problems for us. And we also need a dictionary, which is going to map the island ID to its area. So we're going to say self.island areas is going to equal to just an empty dictionary. And this is one of those grid problems where we're kicking off a depth first search in 4 directions, so we need to define our directions. So we're going to say self.directions, and pretty standard, we're going to have our 4 directions here. So let's just code these out, and those are the 4 directions we can travel in. Now, what we need to do, remember, for the first iteration to our grid, what we want to do is go through and find the area of each island, set its tile values to whatever the current island ID is, and then again, update our island areas with the total area of our island. And remember that essentially this is the same process that we did in the problem finding the area of an island, right? So let's do it. We're going to say for m in range, len grid. We're going to say for n in range, len grid m. We're going to say, okay, if the current value is a 1, that means it's an island value, so that means that we want to kick off our DFS here. So we're going to say if grid of m, comma n equals 1, that means that this is a new island that we're visiting, we want to find all of its tiles. So we're going to say island area is going to be equal to our DFS function, which we'll write in a second, and the DFS function is going to take our grid, and it's going to take our current m and n position. And now that we have the island area, we want to put that into our dictionary. So we're going to say self.island areas of, let's see, self.island ID is going to equal to the island area, so island area, and then we want to basically now increment our island ID. Although because we're using negatives, we're actually just going to decrement it. So we're going to say self.island ID, we're going to decrement it once, now we have a new unique ID for the next time we go through our thing here. So at this point in our function, we're actually going to have all of the areas for each of the islands, and their values will be overwritten inside of the DFS function, which we'll write in a second. So now what we want to do is we want to define our answer, which is going to be max area. And what we need to do is go through for a second time and basically flip each 0 to a 1 and figure out the maximum area we can get by essentially doing that. So let's go through the grid one more time. We're going to say for m in range, len grid. We're going to say for n in range, len grid of m. We're going to say, okay, if the current position is actually 0, then we want to flip it to a 1 and figure out what the maximum area is if we were to do that. So we're going to say if not, grid of mn. So essentially if our current value is a 0, we're going to say the area is 1 because that 0 flips into a 1, so that is at least an island of area 1. And then we want to keep track of all of the distinct surrounding islands touching that current position. It could be the case that, to our left and, above us, so up and to the left of us in the grid, is actually the same island. So we only want to count it once because we're going to add the area of that island, and we don't want to count it twice. So we're going to say surrounding is equal to a set. And now what we want to do is look in all 4 directions, figure out all the distinct islands 4 directionally, and add their areas to us. So we're going to say for m increment, n increment in self.directions. What we want to do is we want to say the new m is going to equal to m plus the increment of m, so m increment, m inc, and we're going to say the new n equals to the old n plus n increment. And now what we want to do is we want to check, first of all, is our new m and n combination, so the new row and column is inside of the grid, obviously we don't want an index error, and we want to make sure that the new row and column position, the value there isn't actually 0. Because if it's 0, we don't care, it's not an island, we can't take its value. So what we want to do is we want to check that, so we want to say if the new position, so we want to make sure we're in the grid, so we're going to say new m less than len grid, and we're going to say the new n is also less than len grid 0, so let's check columns, and we want to make sure the grid, let me just move this over so we can have some space here, grid of new m, new n does not equal to 0, so we want to make sure that the new value of that index, new m, new n, is actually an island. If it's not, then we don't care about it. So we're going to say surrounding dot add grid of whatever new m and new n is. Remember that we don't want to be double counting things because then we're going to get the wrong answer. We only want to sum the areas of the distinct islands that are touching our current position. Cool, so now we've done that, and now we need to actually add those areas. That's all we do.
You're new to programming? It's okay. You'll learn if you, I guess, you just do it every day. It's really like it's like anything in life that you want to learn. Just gotta put in the time and consistency.
What we did is actually just add the IDs of the surrounding areas. Remember that we overwrote the grid position at the index with the island IDs. Now we know all the IDs that are neighboring us because they're in the surrounding set. Now what we can do is actually just add them to our area, which remember is just 1 because we've already done so far is flip that 0 into a 1. So what we want to do now is we're going to say for island ID in surrounding. All we want to do is add to our current area the value from the island areas dictionary for whatever that island ID is, and that's going to be the area of the island that we formed by flipping our current position from 0 into a 1. Now all we need to do is simply check that this is a maximum. So we just want to say max area, which is the variable our solution. We just want to take the maximum of whatever its current value is and our new area, and if our area is greater, then obviously that becomes the new answer. So once we do this process for every single 0 in our grid, what we want to do is actually return our answer. Now here's where an interesting edge case comes up. What happens when the entire grid is 1s? Well, if the entire grid is 1, we'll never actually hit this point here, and we'll never actually end up updating our max area, because the only time this if statement fires is when we're at a position in the grid that's 0. If the entire grid is an island, in this case here, then we would actually just return 0, because max area currently returns 0. So what we need to do is check, actually, have we seen an island? Because if we haven't seen an island, if our max area is still 0 at the end of this double for loop, that means that the entire grid is actually an island, and in that case, we don't want to return 0, obviously that's the wrong answer. We just want to return the dimensions of our grid. And remember, it's an n by n matrix, so we just want to return, n squared. That's going to be our solution. So that's the last thing we have to check. We're going to say return max area if basically max area is non-zero, right? Otherwise, we just want to return the length of the grid squared. And remember, the grid is n by n, so it's just length of the grid squared, and that's going to be our final solution there. So that being said, we still need to find the DFS function, which is actually going to calculate the area. So we're just going to do this effectively because you should already know how to do this from the previous max area of an island. So we have our grid, we have our m position, we have our n position, and essentially what we want to do is we just want to find sum all the areas of all the adjacent points that are part of our current island. So what we want to do is we want to basically just check that we're even in the bounds of our grid so far. So we're going to say if 0 less than or equal to m less than or equal to grid, and so that basically checks the rows. We want to check columns here, so n less than grid of m, and basically the last thing that we want to do is we just want to make sure that we're actually at an island value, right? If our current position is actually 0, that means it's water, and that isn't a valid position, so we just want to exit out of our DFS here because we don't want to be summing it in here if it's water, we don't sum it. So we just want to make sure that grid of m, n actually equals to 1, which is land. In this case, case, what we want to do is, remember, we want to overwrite the current value with whatever self the island ID is, and what we want to do is we want to say area equals 1, and then we just want to go forward directionally and figure out what the area is by basically applying our DFS function to the 4 adjacent tiles to us. So we're going to say 4m increment and increment in self.directions. What we want to do is we want to say area plus equals to self.dfs, grid m plus m increment, n plus n increment, and at this point, all we want to do is return the area, and then for the if statement, basically, if we're outside the bounds of the grid or our current position is water, then all we want to do is return 0, because that's not going to affect our answer. Obviously, adding 0 to anything just returns whatever you added that 0 to. So that is the DFS function. This is we called it in here in the initial pass-through of our loop here. So let me just run this, make sure I have any syntax errors. Otherwise, this is slightly a lot of code. It looks like it's running when you submit it.
There's no way they expect you to do this in an interview. There's no way. This is insane. It's like actually insane. I think I might be done for today, I can't lie. But I really gotta do some systems design stuff. Maybe I just watch
Wealthfront
this.
offers a cash account that has one of the highest interest rates on the market.
Hello everyone, welcome back to the channel. I'm Evan, co-founder of Hello Interview and a former Meta staff engineer. And today I actually wanted to take a step back and make a more beginner-friendly video for you all today. So many of you have seen our system design breakdowns. We're going to do a new one of those today, and it's going to be for the classic question design a URL sorter. It's everybody's first system design question.
And in this video, as I mentioned, I'm going to slow things down a bit. I'm going to teach concepts that we otherwise take for granted in some of our other videos. So if you're new to system design or you're dusting off the cobwebs, this is the place to start. If you like our content, you want more of it, please make sure that you like and subscribe. The increasing number of subscribers is really motivating to us. It makes us want to create more content for you, so make sure you smash the buttons if you haven't already. Lastly, if videos aren't your thing, I've linked the written resources in the description as well. So if you want to watch this whole video, you can just come here and read the written form. There's also tons of other common problem breakdowns over a dozen now on the left-hand side. You can also try all of these yourself with guided practice. And so guided practice is a tool that quickly just lets you walk through designing systems on your own, and then you get this personalized feedback for each step along the process. This feedback was tuned by myself and my co-founder Stefan. So give that a go. And the last thing here is that if you're looking...
I've gone for Python and CSS side by side. I actually don't have somebody to guide. What do you think I'm working in the market, and what should I follow if you have any knowledge? I mean, what's your end goal at the end of the day? Like, are you like you don't care about the language? You know what I mean? Like, at the end of the day, certain companies utilize certain languages to tackle, you know, common problems. If you want to do like web dev related stuff, then, you know, React, TypeScript, that's what I do at my job. If you want to do like more data science related stuff, I think Python's probably better. I guess it really all depends. Like, if you don't even care about what you do, as long as it's just programming related, then I don't think you could go wrong with web dev, because I feel like, well, I don't know. Nowadays too, like if you're trying to future-proof as well, I think being like a machine learning engineer is probably more promising, I guess, in terms of job security. But I think the barrier to entry is a little bit harder because you need to have pretty good math theory. It all depends though, you know. All depends what your goals are, and you know what you're looking for. But I mean, Python's used a lot too, I'd say. C++, even Java. All really depends like what you're trying to do though. You know, all depends.
Or if you're preparing for interviews, the best thing that you can do is mock interviews, and that's our specialty here at Hello Interview. So come on over, do a mock interview with Senior Plus Engineering Manager from your target company, and they'll tell you exactly where your gaps are and how you can improve. All right, let's get into it. Before we start designing our URL shortener, let me take a brief moment to just explain the framework or the steps that we're going to follow both in this interview, and this is also the framework or steps that I suggest you follow for any of your system design interviews. So the first thing that we're going to do is we're going to define the requirements of our system. This is both the functional requirements, or the core features, as well as the non-functional requirements, or the qualities of the system, things like scale, durability, fault tolerance. After we do that, we'll define or outline the core entities. This is a really simple high-level list of the core entities that are going to be persisted and exchanged in our system. Another way to think of this is like the names of the tables or collections that you have in your data model. Once we do that, we're going to move on to the API. This is the user-facing API. It's the contract between your client and your users and your backend service. From here, we're going to skip data flow. This is only applicable to infra-heavy system design questions, so like design rate limiter, design message queue, stuff like that. So not applicable to a user-facing product like a URL shortener. So instead, we're going to write to high-level design. This is where we're going to head to the whiteboard. We're going to start drawing boxes and arrows in order to outline a system where the primary goal is to satisfy the functional requirements that we outlined in one. And so at this point, our system's going to be really simple. It's not going to be able to scale. It's not going to be able to do anything too fancy. It's just going to be able to satisfy those core features that we outlined. But from there, we're going to move on to our deep dives, where things are going to get fun, and we're going to go one by one through those non-functional requirements in order to evolve our high-level design in a way such that it ends up satisfying each of those non-functional requirements. And at the end, we're going to have a system that satisfies all our functional requirements, all our non-functional requirements, and we're going to feel really good when we pass the interview. As promised, we're going to start our design with the requirements of the system. And so the first thing we do is we start with the functional requirements. The functional requirements are the core features of the system. This is where you're going to try to identify the top 2 or 3 features that are necessary and that you will have time to design in your 35 to 45 minute interview. Now, if you're told to design a system that you already know well, then this should be pretty easy. But you might also be asked to design a system that you may have never heard of. In this case, you're going to ask a lot of questions. This is the time where you pepper your interviewer with questions in order to better understand the system that you're required to build. In our case, what is a URL shortener? Well, a URL shortener is a service that converts long URLs into short ones, and then those short URLs will redirect you to the original URL. So you can take this long URL, give it the URL shortener, it returns the short thing, you can put the short thing in your browser, and it's going to redirect you here. Pretty simple. So in our case, functional requirements can always be thought of as like these users should be able to, users can, users will statements. And so what are ours? Well, the first one is that users can create a short URL from a long URL, from an original URL. Perfect, that's our first thing. What's the second thing? Well, users can be redirected to the original URL from the short URL. Easy, right? Those are the 2 core features of a URL shortener. Now I'm gonna add a little bit of flavor that's often added in these questions, and I'll have candidates address if I'm conducting this interview. And that's it. I want to optionally support a custom alias. And so this is that users can come to us with their own short alias. Maybe instead of us generating this random thing, they give us, for example, Evan, and then the short URL becomes /Evan, assuming it doesn't already exist. So we'll support that. Optionally, if they want to provide it. We'll also optionally support an expiration time. And so maybe somebody's creating a short URL for a conference or something, and they only want it to be valid for the week, then we'll expire it after that week if they give us an expiration time. This means that somebody tries to navigate that short URL after the expiration, they'll just get an error or something telling them that it's already expired. So these are the core functional requirements of the system. The next thing you would do is that you would go into the non-functional, what we refer to as the non-functional requirements of the system. Now the non-functional requirements are, instead of being features, and like they are the quality of the system. And so the quality of the system are all those words you've heard. These are like these abilities words, these things like the scalability, the latency, the durability, security, fault tolerance. Is your system compliant? This is where you talk about cap theorem. All of those things. What qualities does the system need to uphold in order to ensure a good user experience and or meet user expectations? And so what you typically want to do when you get the non-functional requirements, and these are hard oftentimes, especially for more junior candidates to think of, is that you should go one by one through those daily statements. Maybe you have a list of them kind of readily on your table as you're going to the interview, and you think about which one of them are uniquely interesting and relevant to this system. And so, for example, the first one we could look at is latency. How is latency important in our system? Well, it's really important that redirection is low latency. And so one system requirement, and these are, instead of users should be able to, the system should be statements. So the system should be low latency on redirects. So if we give a short URL, we should automatically go to that original URL. So not only did we choose the non-functional requirement, but we put it in the context of our system. It's not just low latency, it's specifically low latency on redirects. And we want to quantify it too. We're going to say about 200 milliseconds. 200 milliseconds is a good number here because it's what is the humans perceive as real time. So anything under 200 milliseconds, you wouldn't even notice the difference. 200 milliseconds is like a snap of a finger, it's real time, so it's a good lower bound for us here. So we have one non-functional requirement, low latency on redirects. Another thing that we can think about is the scale of the system. This is the time when I would ask my interviewer. I would say, how large is the system are we designing? How many users? What's the scale of this system? And they might tell you to estimate it, or they might just give you a sense of what the scale is. I typically would do the latter. And I would tell a candidate they should expect 100 million daily active users and around 1 billion URLs that get shortened in totality over overall time. And so that would turn into a functional requirement that the system should be able to scale to support 100 million daily active users and 1 billion URLs. Fantastic. We can do progress in non-functional requirements. Another one that's interesting here, which is a little bit hand-wavy whether it fits in non-functional requirements, but I want to call it out because of how important it is that each of these short URLs or each of these short codes, they need to be unique. So the system needs to ensure uniqueness of short codes. These short codes are these things that we're appending to the end of the URL, right? We need to ensure uniqueness of short codes so that there's no collision, so that people don't end up getting redirected to a site they weren't expecting to go to. So those always need to be unique. That's definitely going to be a core system requirement. And then the last one here that I'm going to do, which typically you might do first, but it's always going to be considered, and that's cap theorem. So really quickly, what is cap theorem? Well, cap theorem is a theorem that states that when considering consistency, availability, and partition tolerance, you can only ever have 2 of those 3 things. Now, partition tolerance in distributed systems, like we're almost always designing system design reviews, this is a guarantee. You have to have partition tolerance because you're going to have partitions. You're going to have different instances, for example, your data, so you're going to horizontally scale your servers. And so the decision really becomes, is it consistency or availability? Does my system need strong consistency or does my system need high availability? And what I want you to think about as you're in an interview is, do I need strong read after write consistency? The way to think about this is, does every single read of my system have to read the latest write, or else the system breaks or fails in some way? So common examples of systems that need this read after write strong consistency are like a banking application or a ticket booking system. The example being the ticket booking system case, if somebody went and booked the last ticket to the Taylor Swift concert in Germany, and then I in America went to book that same ticket, and I went and read the database and it told me it was still available because I didn't have strong read after write consistency, I would book that ticket and I would both show up and we would be fighting for the same seat. That would be bad. This would be like a fatal error to our system. We can't have that. Same to in a banking app. Somebody else trades a stock, especially if it's low float, I, no matter where I am in the world, need to know that stock was traded because it might impact the price before I buy or sell respectively, right? In the case of URL shortener, we need that strong read after write consistency. Well, you can imagine that somebody gives us a long URL, we shorten it, we give them the short URL back. Does anybody who then hits that short URL immediately need to be able to be redirected? We can say no. And the reason we can say no is because, first of all, there's some time that it takes for users to share a short URL with other users and for it to start being used, and that gives us time to be eventually consistent. If for some reason somebody was wicked quick, A, there are ways that we can handle that by making sure they're redirected to that same original node. But B, if they didn't get redirected in that first couple seconds, up to even a minute, who cares, right? We can show them a little error that just says like, we're still saving this in the system. Let's try again in a minute. And no big deal. The world wouldn't end. 2 people wouldn't show up to the Taylor Swift show fighting for the same seat, right? So because that's the case, because we don't need strong consistency, we're instead going to go for availability. And so we're going to say high availability. We don't need strong consistency. Why we don't have to spell that? We don't need strong consistency. Instead, we can handle eventual consistency. So eventual consistency for URL shortening, right? Cool. Okay, so that's our non-functional requirements. The last thing that I'm going to say here is that MakeGuide will instruct you at this point into going back to the envelope estimations. So you come here, you do back to the envelope estimations, you end up talking about things like scale estimations, latency estimations, like total storage estimations, whatever. This is fine, you can do it, but I'm going to suggest that it's useless. Estimations and calculations of modeling system design is very important. But doing it upfront like this, I find, as an interviewer, is almost always useless. Candidates will do some basic math about storage, latency, etc., and they'll look at me and they'll go, okay, yeah, so it's going to be a big distributed system. And it's like, you kind of do that already. Then there's 100 million daily active users and a billion URLs. You're not telling anything new. And you're not going to change your design based on information. You're always going to do a distributed system. And so what I argue is that doing math for the sake of doing math is not useful. Instead, you tell your interviewer, I'd rather not do math up front, and I'm going to do it during my high-level design, my deep dives, if I need it to make a decision. And so the key here is that you're going to do calculations when the result of those calculations will directly inform a direction or decision that you're going to take in your design. And doing it up front like this, in my experience, does not satisfy that. Next up, we go into the core entities of the system. Now, the core entities, as I mentioned, these can be thought of as basically the tables that you're going to have in your database. This is the entities that your system is persisting, storing in the database, and exchanging by the APIs, right? And so core entities, as I suggest, as we suggest in Hello Interview, you start by just listing off these entities. Don't worry about the full data model yet. You're going to get that later. I would communicate this proactively with your interviewer. I would say I'm not going to do the full data model just yet. So I'm going to list off these core entities, and then like in my high-level design, I'll be more explicit about the fields or columns for each of them. But in our case, what do we know we have? We have original URL, we have short URL, and then we have a user who creates them. These are the entities in our system. Pretty straightforward. And the reality is that this system is so simple that you could outline the data model here if you wanted to. You probably know it at this point. The reason that we don't yet is because for more complicated systems, it's oftentimes too early. We haven't had a chance to think through our API and all the requirements that would have us understand what the full data model would be. But in this case, it might be fine. I'm going to go with this, and this is a good enough core entities for now, which takes us into our API. The API is where, again, we define that contract between our client or our users and our system. And the way that I suggest to go after the API is very methodically. You're just going to come up here with your functional requirements. And in most cases, it's a one-to-one mapping between a functional requirement and an API. Not always. Sometimes you have like 2 or 3 API endpoints for each requirement, or maybe you don't even have an API endpoint for requirement. But you should come up to this list and you should say, the first thing I need to do is users should be able to create a short URL from a long URL. Okay, let me make sure that I have an API that supports that. So in doing so, the first API we need is to be able to shorten a URL. So this is going to be a post endpoint to some URLs resource, and it's going to return a short URL. We're just going to reference here our core entity. Right? It's going to return a short URL. And the body here is going to be what? Namely, it'll have an original URL, again referencing that core entity. It could have that optional custom alias, and we use question mark in order to indicate the optionality there. And then we can also have optionally that expiration time. So the expiration time, right? So there's our first URL, our first API endpoint, which is going to allow us to take an original URL and return a short URL. When you're doing these system design reviews, you oftentimes will use REST APIs, though not always. When you are using REST APIs, a couple things to think about. You want to make sure that you get your verb correct here. You have post, put, patch, get, delete, etc. Most often, you're just going to use post when you're creating a new resource, put or patch when you're updating a resource, delete of course if you're deleting a resource, and then get if you are, quite obviously, getting or fetching a resource. So make sure you have those down. And then when it comes to these paths, you typically are going for a plural noun. And so to be honest with you as an interviewer, I don't care about all of this. I think this is like kind of silly semantics that are easy to change, figure out. They're not most interesting part of the design. Especially at the lower levels, you'll have like what I'll call RESTful API zealots. Interviewers really care about this, and so I just want to be aware and considering things appropriately. Okay, so that's that first API endpoint, right? We just satisfied that first functional requirement. The second one is users should be able to be redirected to the original URL from the short code. Okay, so we need to have an API endpoint for redirection. So how is this going to work? Well, we're going to have some get endpoint, and it's going to go to slash like our short code, or to use our core entity, it's just going to go to our short URL, and then it's going to return a redirect to our original URL, right? So it's pretty straightforward. Now, in case this isn't obvious, the way that these systems work, of course, is that when you run this get, and we'll get into this in a moment, when you run this get, you're hitting our server, the server that we own, our URL shortener, with that short URL and that short code. And then we can take that code, figure out what we need to do with it, we'll get into that later, and then issue the redirection. But that's how this ends up working. So here are API endpoints, super simple. We double check. We have an API endpoint for each of our functional requirements. These fully satisfy those requirements. We feel like we're in a good spot, and we're ready to move on to the next section. So at this point, we've done all the setup work. We have a really clear understanding of the system that we need to design. We have core entities that are persisted in exchange, and we defined our contract with our backend between our client and our server. And so the next step is to come over here and do our high-level design. So things are more fun. We get to the whiteboard, we get to draw, and our primary goal again is to just satisfy these core functional requirements. So we're not going to worry about scale or meeting latency or ensuring uniqueness or availability or any of these things yet. We're going to do that later. We're just going to get a simple design down that works. And by following this framework, our mind is just working linearly. So even if we're given a problem that we haven't seen before, we can just build the design up step by step by step. Okay. So when it comes to high-level design, here's how I recommend you do it. You come over to each of the APIs, and you start with the API, and you draw up the system that's necessary in order to satisfy the API. This is equivalent to going step by step through each of the functional requirements, as you are note. But by doing it for the APIs, you can be really clear about the data flow and about what needs to be input and output of each request, and how the system transforms those appropriately, if you will. So let's come over here and let's draw this out. I'm going to start simple, and I have a given client. This client here is just maybe like the website, right? Pretty simple. And then I also have a primary server. So this is going to be the primary compute resource in my backend. And I'm also going to add a database. I'm going to add a database. And so this is a very classic design pattern, just a client-server database relationship. The client is going to make a request to your backend server, or your server is going to do something, persist in your database, and then return it back to the client. And so in our case, what we're considering right now is what happens when a user tries to shorten a URL. They're going to make a post request to slash URLs, and then we're going to return to them a short URL. Well, how are we going to do that? We're going to do that because they're going to make that API request here. The API request is going to be, get short URL. It's going to hit our primary server. Our primary server is going to have some magic black box that creates short URL. We'll talk about how it does that later. We'll stay abstract for now. So it's going to generate that short code, and then it's going to come over here and it's going to save it to the database. Make that a two-way arrow. This one should be 2. Cool. So it's going to come over here, it's going to save it to our database, and then return it back to the client. Well, what is it saving to our database? We probably now define some data models. Instead of having separate entities or separate tables for the short URL and the long URL, which we could do, I'm just going to combine them in this case into one because of how simple it is, and this is going to make more sense. So I'm going to have a URL table, and this URL table is going to have the short URL, and it's going to have the long or original URL. It's probably going to have the creation time, and the user ID, a forwarding key to the user that ended up creating this. And then subsequently, I'm going to have a user with the user ID. I'm not going to outline anything more. Of course, the user table will have an email, a password hash, solve all these different things. Who cares? I see some mechanics get distracted by those things in an interview. We're focusing on the core functionality here. All of that is auxiliary. And so maybe I just do this. Of course, I'll do additional editing. Cool. And so we take a look at that first API endpoint that we had, post to URL, return a short URL. Here's how it's going to work. The client is going to post to our primary server. It'll create a short URL. It'll store that in the database as a mapping between the short, the long URL, the creation time, and with the user ID, and it'll return that short URL back to the client. Easy. We got it. First one down. Now the second one is that the user needs to get that short URL and be redirected to the original URL. And so how are we going to do that? Well, now we have an additional thing here. We have this redirect, which takes in the short. This one's taking the long. And so that's going to come from our client. It's going to hit our primary server. Our primary server is going to look up long from short, right? So it's going to go over our database. It's going to query it based on that short URL. We're probably going to want to make that our primary key. It's going to query it based on the short URL. Then it's going to return the long URL back to the user. And it's going to return this back to the user with, importantly, a 302 redirect. And so a 302 redirect is just the HTTP status code, which tells the browser, I want you to take this URL and automatically navigate to it. I want you to automatically navigate to this URL. And when it comes to redirects, we have two options. We have a 302 redirect and we have a 301 redirect. These are both different HTTPS status codes. And so in the case of a 301 redirect, this is a permanent redirect. And what it basically means is that your clients, your browser, DNS servers, potentially, they can cache this redirect. And in the future, they might not even need to go to your service. They're just going to redirect it immediately based on the cache. In the 302 case, this is temporary. And so it's never going to be cached. They're always going to come to us first. We're going to look it up and then we're going to send it back. And so there's a conversation that you have with your interviewer at this point, potentially about whether 302 or 301 makes more sense. Now, it depends on your requirements. I suppose in our case, we don't care about analytics, which is what would make the 302 the right answer here. Because in the case where you have analytics, you can show users how often the short URL is being queried.
You would want to make sure that it always comes to your server, because then you can log and you have an understanding that this redirect was requested. In the 301 case, you're not going to get that. You're not going to afford that ability. It's not going to hit your server, so you're not going to be able to log in and compute your analytics. Now, this permanent redirect would be better if we were worried about compute cost. If we're worried potentially about not having to scale the server in the future, then by having it be permanent, it's handled by caches elsewhere and may never even hit our backend service in the first place. That's pretty nice. And so there's pros and cons here. Typically speaking, you want to go with the 302, even the cost to how many servers you may need, because it allows you to understand if things are working. Even if you're not showing users analytics, if that's not a core requirement, you would be tracking that internally as a platform, as a product. And if you saw things drop off a cliff there, well, you would know something probably broke on a client, and we're not getting these requests anymore. And so by making it 301, you lose that visibility. And this is the argument that I would make in an interview, and why I would decide on a 302 redirect here. And so the server will respond to the 302 redirect with the original URL, and the client will then navigate to the original URL, and they'll be viewing that original website. Awesome. So super simple. We went through each of our APIs. We now have a really high-level design that satisfies both of our core functional requirements. I suppose with that being said, as I just went back here and checked, as you should do too, I know that we actually didn't discuss two parts of that functional requirement. That's the custom alias and the expiration. So let me come back and amend appropriately. We're going to add here, that short URL / custom alias. This could be either of those things if they provided a custom alias. And then we're also going to add that optional expiration time. So an expiration time here.
And so now what a user would do is they give us a short, if they wanted to get a short URL and give us a long URL, and they also give us a custom alias, we would need to first look up in the database, does that custom alias already exist? If no, add a new row where the short URL is a custom alias, and return that back to the user. Easy. And then in the case of expiration time being provided, we'll make sure that we add it here. And then on the redirect call, when we come to look up our long URL based on the short URL, we'll also check the expiration time. Is the current time greater than the expiration time? If so, return an error instead of 302 redirect. Okay. With that being said, now we have a high-level design that satisfies each of our functional requirements, and it's time to go deep in order to expand this design to support each of our non-functional requirements. So we move on to deep devs. We're going to come over our non-functional requirements, and we're just going to go one by one through them, evolving a simple high-level design such that it meets each of these non-functional requirements as well as the functional requirements that it already satisfies. And now, if you all allow me, I'm actually going to take some liberties here. I'm going to start off with the third one, ensuring uniqueness of shortcodes. And the reason I'm going to start off with that one is because you'll realize that in our high-level design, we intentionally overlooked kind of the core of this problem. We black-boxed this create a short URL. That's the hard part. That's the interesting part of a URL shortener, and we just hand-waved it. Now, we did that intentionally. The reason we did it intentionally is that a common mistake I see candidates make is that they go too deep on any given part of the design too early, and all of a sudden time runs out, and they didn't even get a chance to satisfy all of the functional requirements of each of their system. This is a mistake. And so you want to be pretty high level. Make sure that you have the base down. Make sure you satisfy those functional requirements, and then come back and go deeper. And that's exactly what we're doing here. So I told my interviewer, I said to my interviewer, I'm black-boxing this, but now I'm going to come back to it. And now let's do exactly that. So what do we need? We need two things when it comes to creating a short URL. Well, maybe we need a couple of things. We need the creation to be fast. That's reasonable. We need it to be unique, and we need it to be short. Those are the three things that we care about. How short? Well, we can ask our interviewer, or we could guess, but typically we're talking in like this 5 to 7-ish character range, right? So 5 to 7 characters maybe is short enough. And so let's talk about some options that we have here. In an interview, you do exactly this. You kind of work your way up, building from the most simple solution to something more complex, certainly if time allows. So the first thing that we can do is that we just take a prefix of the long URL, the input URL. So any given long URL that comes in, let's just chop off the first 5 to 7 characters, stick that then as our short URL or short alias or excuse me, our short code, and append that to the end of our www.bit.ly/that prefix. Right? Now this is obviously bad. Why is it obviously bad? Well, because there are tons of URLs that share the same prefix. What about every single URL at www.twitter.com or www.facebook.com or any of these different common URLs? They're all going to share the same prefix. And now we don't have a one-to-one mapping between short and long URL. We have a one-to-many mapping. And this means that if you give us one of those prefixed short URLs, we have no idea which one of the thousands, hundreds of thousands of long URLs it actually maps to. So that's our idea. Don't do it. The second thing that we could do is we could use a random number generator. This is my third idea. So this is a random number generator. And so we ask ourselves, like, how large can this number be? How large should this number be? How large would this number need to be? Well, if we come back over here, we're reminded of our scale that we're going to have a billion URLs. And so this means that this random number needs to be at least between 1 and a billion. Of course, if it's just between 1 and a billion, our collision rate's going to be really high, so we might want to be higher than that. But it needs to be at least that. 1 billion is 10 to the 9, or 10 characters, right? 10 characters. That's more than our 5 to 7. That's too many characters. And so we'll need to do something a little bit more sophisticated in order to compact that. We can't just append 10 characters to the end of this thing. And we need at least 10. Remember, we probably need 11, 12, 13 in order to make sure our collision rate is lower. But here's what we can do. We can do something called base 62 encoding. And so base 62 encoding is basically thought like a numbering system, like 0 all the way to 1, 2, 3, 4, 5, 6, 7, 8, and all the way up. But instead, we're going to incorporate the alphabet. And so the way the numbering works is that we go from 0 to 9, and then we go from A to Z, and then we go from A to Z lowercase. And so what this means is that 10 is actually A, 11 is actually uppercase B. And it means that any given character can now encode 62 options, as opposed to just 9 or 10, like in the traditional base 10 encoding, right? So we can take a large number and then base 62 encode it. And so now how large would we want this to be? Well, if we had, for example, a code that was like 6, let's go right between our 5 and our 7, then it would be 62 to the 6 possible combinations. 62 to the 6 is 56 billion, about. And so that's pretty good. We have like a decent amount of space there. We can randomly choose a number between 0 and 56 billion. We can base 62 encode it, and it's going to be a short code. It'll be like 6 and base 62 encoding. But what about our chance of collision? What is the chance that a random number between 0 and 56 billion, when calculated a billion times, ends up colliding? Well, you might be surprised by this, but the collision probability is actually really high. This is oftentimes referred to as something called the birthday paradox. I'll write that down in case anybody's interested in reading about it. This is the birthday paradox. And it's this counterintuitive probability problem that states that there's actually a 50% chance that 2 people in a group of only 23 people have the same birthday. I'll say that again. You can see why that's so counterintuitive. If you have 23 people in a room, there's a greater than 50% chance that at least 2 of them share a birthday, despite there being 365 days in a year. Now, the formula that is used to calculate that can be used to calculate the probability of a collision on 56 billion randomly generated things as well. And you wouldn't need to know this in system design because I thought it was interesting. I went out and I did this. And it turns out that out of 8 billion, or excuse me, 1 billion random generations, there's an estimated 880k collisions that would happen here. So that's a lot. That's like a decent number of collisions, right? It's depending on how you define a lot. 880k over 1 billion might not be that many, but it's certainly a large enough number that we would end up with more than 1 happen. And so how do we address this? Well, one thing that we can certainly do is that we can take this approach. We can random number generator, base 62 encode. Yes, there might be a collision, but what we'll do is before saving it to the database, we'll come over to our database and we'll read the short URL, see if any exists like this already, and only if they don't exist, write to it, update it. So we just introduce another read. Instead of calculate the short URL and save to the database, it's calculate the short URL, check, and then save to the database, right? So that's totally possible. So basically we just need to check for collision first. Is that a big deal? Not really. It's an extra read. There's some consequences to that, but no, it's not a big deal. That's one option. Another option is that we could hash the long URL. This is a common one that I see a lot online and that candidates often raise. So they can take that long URL and they can call some hash function. And so maybe that hash function is like MD5, something cheaper like mirror hash, something like SHA-256 for graphically secure, whatever. But you get a long URL, and then you end up getting some thing, some output, right? Some hash, and you would take that hash, and you would base 62 encode that hash again, right? And then you would slice it to take just those first 6 characters. So that would be the operation that you would do there. Now what you end up with is 6 characters of base 62 encoded. So you end up with the same thing that we end up with the random number generator. And because of how hash functions work, right? A hash function, despite it being deterministic, has that waterfall effect such that if you change just one bit on the input, the whole hash should change significantly. And so increasing the randomness of the hash that's generated. And that property means that the output is actually exactly the same as the random number generator. It's literally the same thing. It's sure there's 56 billion chance, 56 billion possible combinations. The chance of collision is exactly the same. So same as above. Again, this would totally work. It would work exactly the same. We just need to make sure that we check the database first. Can we avoid checking the database is the question. The answer is yes. Is it a better approach? The answer is maybe yes. But what we could do is we could use a counter. Like why introduce this randomness in the first place? Why doesn't the first person who comes to us just have short code 1, the second person have short code 2, the third person have short code 3, and so on? And so we can just have incrementing a counter. We can just increment the counter for each new short URL or each new long URL that needs to be turned into a short code. And then again, we'll base 62 encode. We'll always do that so we can kind of make this space more compact. And so this allows us to get up to that 56 billion with 6 things, but we're guaranteed to never have a collision because we're always just linearly increasing. There's a sequential nature to it, right? We're gonna go 0 all the way to 9, and then a capital A, and then a capital B, all the way through until eventually we have 6 characters about base 62 encoded. And so this is great. And maybe what we can do here is to visualize this. Is I'm gonna expand this guy up like this, and we can add in here like some counter. So there's some counter in here, which we're just always going to go grab the next count. What's next? Right, grabbing a count is fast. It guarantees that it's unique, and by base 62 encoding it, we guarantee that it's short. It's not without its flaws, though. So there's a predictability, which is bad for security. And so what this basically means is that anyone who wants to know our short URLs can. They can easily know how to count, and they can easily know how to base 62 encode. And so not only can our competitors know how many URLs we've shortened by just continuing to call our service until they end up not getting a short URL that converts to a long URL anymore, but they also can just like scrape all of the long URLs that we have, right? By just calling the short URL with that new incremented code each time. And so maybe this is a problem, maybe it's not. Like, this is a product decision. We could say when users go to create a short URL, like a warning, like these are not don't shorten private URLs, right? Like, we're not responsible for this. That's one option there. We can of course have rate limiting, so our competitors can't just come and like scrape and grab all of these URLs if they want to. But we also could do something more sophisticated, and that's just not let this become a problem in the first place by introducing something that's oftentimes called a adjunctive function. And so you don't need to know this again in system design review. I think it's just interesting. If you brought up these facts, they'd probably be impressed, but you don't need to know this. Adjunctive functions are functions that just issue a 1-to-1 mapping. And so there are libraries. One of the most popular ones is squids.org. You can look it up if you're interested. And it takes a number and then it returns to you a hash that looks exactly like a 62 encoded string that looks exactly like the short URLs you see on Bitly. And it can take that number that you provided and then one-to-one map it by some obfuscation, so that you can no longer incrementally know how to get the next URL if you're a competitor hacker or anything like this. So these bijective functions exist. It's worth you looking up on your own. I'm not going to go into more detail, but that's one option there. Now the nice thing about this counter code, of course, is we don't need to do the read, right? We know that every single one of these is unique. So now we get the counter, we run our bijective function if we want to, and then we go store that shortcode in the URL table, and we're good to go. The last thing I'll say here is that you're probably thinking to yourself, oh no, this isn't great. Why do you have a counter on a single server? You're right. We'll talk about when we get to scale. But for now, here are your options in order to create shortcode. Both 2 and 3 are totally realistic. You can provide these in an interview, and it should totally be passing. You'll just need to call out the need for that collision check. 4 is an option I think that I like in this case because it doesn't require that additional check. But ultimately, there's very small differences between them. Let's come back over and look at what non-functional requirement we should go into next. So I'm going to go back in order now, and I'm going to jump into low latency on redirects. And so how can we make this redirect as low latency as possible? Right now, what is it that we have to do? Well, the client has to make requests to the primary server. The primary server needs to look up that short URL on the URL table, return the long URL, and that long URL needs to return to the client. Now, the expensive part of all of this is the database lookup. That's what's going to take the most time. And now, without any indexing, I'll explain indexing here in a moment, but we have 1 billion rows here. And you would need to look at every single one of these rows and try to find the short URL that you're interested in so that you can return the long URL that it maps to. That would obviously be prohibitively expensive. It would take a really long time to do. And so the common thing that we do in databases in order to make these queries and these lookups more efficient is we use something called indexing. And so each URL table you can define a primary key. This is true of most database systems. Now, this primary key does a couple things. One, it enforces uniqueness, which is good in our case certainly, but it also ensures that an index is automatically built on that column, right, on that primary key in the table. And this index is typically kept in memory, not always, but you can think of it as this thing that's kept in memory that is a pointer to a location in disk. And so instead of us having to go to disk and seek and look for it through all the records in order to find the short URL, we go to memory, we look at this index, and we ask it, hey, where is short URL 123? And it's going to tell us where in disk it is, and we can just seek to disk, or we just go exactly to that place in disk, find the long URL, and return it. Makes it much, much faster. Now, when you have a primary key is something like Postgres, let's say that our database here was Postgres, then it uses a B tree of the index. A B tree is a self-balancing tree, not like it is a self-balancing tree. If you've been studying for your coding interviews, you know plenty about trees. And so it's going to make this log in. Oftentimes actually much quicker than that. There are quite a few optimizations that exist in modern databases nowadays, but that's what's going to happen. It's going to make this look a lot faster. Now, you do have an option of additionally creating a further index, basically a second index on the short URL, which can be a hash index. And this would be O of 1. It would hash the short URL and point directly to where the row is for us to get the long URL. You can totally do this. Realistically, you don't need to. These B trees in Postgres, for example, and all these modern databases are so well optimized for these like equivalency lookups that it would effectively be the same. So not something to actually worry about. Now, we're still going to disk. We solved one part. We don't have to go to disk and then read all the records in disk. We're going to go to memory. We're going to use that index to find where we need to go in disk. We'll still need to go to disk and then back. Realistically, SSDs are really fast nowadays. So this wouldn't probably be a problem. But we can certainly make it faster by never having to go to disk in the first place and only ever going to memory. And so while we're going to index first, that was our first option. We got that here index. Our second option is that we're going to add cache. And so we can use something like Redis. We can use memcached, we can use any in-memory cache here. And what this cache is it's just another server, just another computer somewhere, a separate instance, a separate computer running, and we're just going to utilize its memory. We're going to utilize its RAM in order to be really quick here. And so we're going to make this be a read-through, least recently used. So read-through, least recently used cache. What the heck does that mean, right? It means that any time that we want a short URL or we want a long URL for a short URL, we're going to look in the cache. And if there's a cache miss, then we're going to get it from the database, update our cache, and then return it. That's the read-through nature. The least recently used is just saying if this cache is full, then our eviction policy is that anything that hasn't been touched lately, kick it. Because the reality of a system like a URL shortener is that there are some URLs that are really hot, they're getting called all the time. But after a couple weeks, months, no one can use the old URLs anymore. And so there's no reason for us to have them cache. Their lookup might take a little bit longer the first time. Who cares? And so caches like this are oftentimes just key value pairs. That's at least most common when I say oftentimes. And so in our case, the key is just going to be that short code or that short URL, and then the value is just going to be the long URL. And so it's going to be really quick in memory. We'll look up if we have a hit. If we have a miss, then we have to come to our database, look up by the index, place in the cache, and then return it. But the subsequent call will be O1 again. So that's what we can do there. Great option. Now there's one thing we can do further. I would actually stop here and argue that this is best for some of the reasons, the arguments that I made when it pertains to 302 versus 301. But we could also cache in a CDN, a content delivery network. What these are is like they're little edge servers that are geographically located all over the world. So you can imagine our primary servers maybe sitting there in California, and you're trying to request a short URL from China. Well, there's a lot of latency required in making that request all the way from China over to California. And so CDNs are these servers that are all over the world. And the user then would hit that server in China, and we would have cached on that CDN any responses to any of our, for example, API requests to redirect to a longer URL from a short URL. There it is, right? So we can do that. But the problem is it's going to hit that CDN and then just redirect the user. It's never going to come to our primary server. So the same issue we mentioned with the 302, 301 redirect, which is that in the case of the 301 redirect, it's a permanent redirect, so we never hit our primary server, and we don't know if our service is, well, like working. And so if we care about knowing if our service is working and logging analytics, then we would use CDN. If we don't care about that, then we can use CDN, but we can also use the 301 redirect, and then we'll just have less things come to our primary server, we have more caching at the edge, both the user's browsers, DNSs, and CDN respectively. So good discussion to have with your interview. This is kind of the essence of these system design interviews. There's no right or wrong answer. It's trade-offs, it's discussions, it's weighing different priorities. And so something important to note. Heading back over our non-functional requirements, we can do our next one, which is scale to support 100 million daily active users and 1 billion URLs. And so when we talk about scale, we want to work our way typically left to right of our system and see where all the bottlenecks would be. All of our services here, all of our components, how do they need to scale? So I'm going to move some things around a little bit so that we have room. But the first thing we're going to look at here is our primary server. And so does our primary server even need to scale? Well, we said that we had 100 million daily active users. Now let's just say that each one of those daily active users does 1 redirect. This seems normal. Maybe it could be 2, maybe it could be 3, change your estimate. But I'm going to say the average is about 1 redirect. And so 100 million is the same as 10 to the 8th. When you're doing math in a system design review, I suggest you use exponents like this because it makes math a lot easier. Watch this. So we have 10 to the 8th, and then there's 100,000 on average, not on average, but rounded up, seconds in a day. Right? So that's 10 to the 5. And so 10 to the 8 divided by 10 to the 5 is just subtraction on the exponents. So 10 to the 3. In other words, 1,000. So we have 1,000 requests per second. Okay, that's if it's evenly distributed. But we want to handle some peaks. So maybe we multiply by 10, or maybe we multiply by 100. In either case, we're somewhere between 10 to 100k requests per second being our peak here. So we do that math pretty quickly. It's kind of a handy tool using exponents in that way. And so then you start to build up some intuition about what is a lot. And so an EC2 average instance, like a T3 medium, can handle around 1,000 requests at a time. I say around. This is intentionally hand-weighted. Like this depends on A, how computationally expensive these requests are, how much memory is being used, how much CPU is being used, how large the payloads are, how much bandwidth is being used. Like these numbers are very rough. But in an interview, you can use that roughly. Like 1,000 requests concurrently is reasonable enough. And so we can't handle this in one instance here. If this was just one server and it can handle 1,000 requests per second, and we have 10k or 100k, we obviously need to do something different here. And so we have two options to us. You probably read about these. The first is what we call vertically scaling, and this is just making this box bigger. So like box plus plus basically. And when I say box, of course, is the server. Just some terminology there. And so we can go to a bigger instance instead of T3 medium. We can pump it up to something that's more CPU, more memory, can handle more bandwidth, like a bigger box. That's one option. It's more expensive. Another option, this one's the most common one, certainly in system design interviews, is that we scale horizontally. And that means that we just have more of these, and that each request that comes in goes to one of them, right? And so that's a really good option, and the option that we're going to take here. We're going to scale this horizontally. But one thing that's interesting to note is that there are a lot of reads in our system, 100k writes per second for that redirect. But this get short URL, we can imagine there's far fewer of those. Like there are very few people who are trying to actually create a short URL every day. Maybe it's 1,000th of the amount of people here. There's like 1 request per second. It's not a lot. And so that doesn't need to scale a lot. The reads need to scale a lot. And so as a result, what we can do here is something kind of interesting, which is that we can evolve our design to be a microservice architecture. And in doing so, we're going to have two separate services, both of which are scaling horizontally. We're going to have one here, which is our read service. This one's going to be responsible for the redirection, and one which is our write service. This one's going to be responsible for creating the short URLs. And then in doing so, we're going to introduce a new component here that we call an API gateway, and it's responsible for being the entry point. So the API gateway gets a request from one of those API endpoints that we define, and then it's going to determine based on that API endpoint which one of these services do I go to, which one should I route this request to, the read service or the write service, respectively. And then the write service, of course, we're going to do this. let's just tie everything together here. We have this is only on the read service, and then this still goes through here. Yeah. Or maybe you can make this abstraction like this if you want to, since it's a read through, but in any case, kind of the same thing, just a little bit of layered abstraction there. Okay. And so now we split this up, and what this means is that this read service, we're going to scale this one horizontally, we're going to have a lot of them, bang, 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 and we might have far fewer of these write services, and it forces us to do so. Now, let me just note that this is true, and it would be a good thing to say in your system designer review, but there's like a very little bit of code happening on both of these boxes, and the reality is like splitting this up into two means that you have two different services to maintain, and it's probably overkill. There's no right or wrong answer, but I just want to call that out. You very well could just keep using the same box and scale them the same, but it's a trade-off away. This is totally a valid option too. So feel free to discuss it in your interview. Now, with each of these services, when it comes to their scaling, nowadays this is like all handled for you on the modern cloud infrastructure, whether it's Google Cloud or AWS or Azure or otherwise, and it's just auto scaling. And so you can have these EC2 instances or in AWS world, and you configure memory in CPU units. So you basically say if 75% of my cluster's memory is used, or if 75% of my CPU is used, throw up a new box. And then if less than 20% is being used, take a box down. And these things will just scale automatically. And yes, technically, of course, there's a load balancer here in front of them that's taking these requests and then just routing them with round robin or however else you configure it within your cloud dashboard. And it's routing to each of the boxes. But that's how it works in practice nowadays. Like, you don't actually control the up and down. It's all auto scaling. So that's something that's worthwhile to know. Okay, so that's how we scale our services. Now with that write service though, we have an issue. Remember we had that global counter here, or we had that counter here. Now this counter, if we have multiple of these write services, we can't have two different counters. They're not in sync. Like they both start at 0, and then they go 1, and now they're 2 1s, they're 2 2s. You get the picture, right? So this isn't gonna work. And instead we need all of these write services to agree on the same current count. And so what we need to do is we need to pull this counter off of the instances. Basically, that counter can't be in memory anymore on these particular servers. We need what we can call like a global counter. And so we can have a global counter here. And this global counter again could be Redis, for which it could be the same instance too. I'm just drawing this separately to make it easy to see. And now they're both going to ask this global counter for what's the next count. And it just keeps a single count here that goes from 1 to 2 to 3, you get the picture all the way up, right? And so in Redis' world, Redis has an inker, which is a command that's just going to increment the counter. You can have that counter here in memory. And because Redis is single threaded, you don't worry about any concurrency. It's single threaded, so we're going to do one inker at a time. It's wicked fast to memory, and then we're going to do the next one. So the count is always increasing. Now one thing I'll mention just quickly is that this means now that in order to get the count, you got to go somewhere else, make a network call, get the count, come back, do your calculation, send it to the database. You got a step here. And so one thing we could do, which is kind of cute, is that when a server comes online, we can request like the next 1,000 counts, for example, and then keep all of those in our internal memory, and then just be using those until we need to request the next 1,000 counts. And if the server goes down before we use all 1,000, no big deal. Like those are lost forever, those counts, but it's fine, right? We had up until it was like 3.5 trillion until we needed to add the 7th character there. So we can afford to lose some. There's no big deal. But this is how this would work. I'm gonna remove that, and you guys need to remember that these are both horizontally scaled, respectively. Okay, and what about the database? So let's head over this way now. How does this guy need to scale? Well, again, let's do a little bit of math here. Maybe I'll do it right here. So we have a short code that's like 8 bytes. We have a long URL. Maybe that's like 100 bytes. We have a creation time. Those are always 8 bytes. We have an optional custom alias. Maybe that's up to 100 bytes. That'd be crazy though, because she's small, so that's on high end. An expiration time 8 bytes. This is 216 bytes, 232 bytes. Let's just round up because maybe we want to throw more stuff in there. Let's say 500 bytes. And so we have 500 bytes times 1 billion rows, and so that ends up just being 500 gigabytes. 500 gigabytes isn't a lot. Modern SSDs are in like the hundreds of terabytes. So 500 gigabytes is nothing. So we can just have a single instance of our database. It's no big deal. The only other thing we'd be concerned about is the read throughput. Like our database handle read throughput, and we put most of the reads on Redis anyway in our cache. So our database is chilling. It's good to go. Now if we didn't scale the database, then we would shard probably by our short URL. And now we just have multiple instances of our database, and where the data was stored would be based on like take your short URL modulo 3 and store on those databases. That's kind of how it works. But in this case, we didn't need to. We did the math and we proved that it doesn't matter. And so at this point, our system is fully scaled. Coming back over, the last thing that we have is high availability. Now most of what we've done by having the auto scaling, by separating these and scaling them independently, horizontal scaling, we're at this point largely available. There are some things we want to consider, like Redis here. We would want to make sure that we probably have. Honestly, I don't care. Actually, if Redis goes down, it's fine. It's read through, so we'll load it back up at the same database. We'll be slow for a little bit. No big deal. If the global counter goes down, that'll be a problem. So we want to have some high availability modes here, which basically means that we have some redundancy. We can also periodically snapshot the count and save it to disk. If you want to look up Redis high availability mode, it'll explain to you more about how that works. That's a configuration here. In the database too, we can have some replicas. So maybe we have a single replica. We frankly probably don't even. Having a single replica would be good because the database went down. But we're also just going to take snapshots every hour or so. So snapshot of the current state of the database stored in something like S3, a big cheap blob storage. Now if the database ever goes down, we just pull it back up. Having that replica there means that one database goes down, we can just point to the replica and it can be in charge for a while until we get our snapshot back up. But that should satisfy our high availability in this case, no problem. So at this point, we take a look back at our requirements and we satisfy all our functional requirements when we do high level design. We now satisfy all of our non-functional requirements. And we look at ourselves and we say, I nailed it. I passed this interview. I crushed it. I know I crushed it because me and my interviewer agreed on the requirements and I have now completed my design satisfying all those requirements. And so I'm feeling really good. You should be feeling really good. Hopefully you learned a lot as well. So there you have it. I hope you all learned something today, especially if you're new to system design. I hope you found this useful. We're going to be back for a regular scheduled programming. Don't worry, some of those more complex problems and breakdowns coming out in the near future. As always, if you have questions, feedbacks, things that you think I did wrong, please go ahead and leave a comment. I'd love to hear from you and I get to as many of those as I can. So don't hesitate there. And of course, don't forget to like and subscribe. All right. Good luck in your upcoming interviews. I'll see you all soon.
Earn 100,000 points into 5.
That was a good video. I think it was well done. I think he explained all the concepts in a very digestible way, I'd say. All right, chat. I think I'm gonna end today. I'm feeling tired. I don't think any more studying is gonna help. So I'm gonna call it there. Everyone have a good night. Everyone take care. And I'll see you guys next time, all right? Good night, everyone. Peace, peace. Peace, peace.